Hello there, and welcome to Science for Sleep, where curiosity slows down, the universe leans in, and we let the big questions take their time. Tonight we're setting out toward the furthest edges of everything, or at least as far as the human mind and science can presently go. We're going to talk about limits, not the sort that tell you when to stop driving too fast or how much luggage you can carry on a plane, but the limits the cosmos itself seems to enforce. These are the boundaries that physics has drawn in the sand, saying in one way or another, this far, no farther. Some are so immense they're almost beyond imagination. Others are incredibly small, fleeting or subtle, yet all of them shape the way reality unfolds. Before we head that way, I'm curious. Where in the world are you listening from right now? Is it night for you, the air calm and quiet, or is the day still unfolding outside your window? Are you winding down, maybe letting your thoughts drift a little looser, or are you in the middle of something and using this as a pocket of calm before moving on? There's something comforting in knowing that no matter where you are, we're sharing this same stretch of audio together, even if the moment you hear it and the moment I recorded it are separated by hours, days, or years. The edges of the universe may be hard to define, but the edge of this moment is right here, where your mind meets these words. If you find it relaxing to wander through big ideas at a slow pace, letting them settle in without rushing, it helps this quiet corner grow when you like the video or subscribe. I'm always glad when someone new finds their way here, someone who's looking for both knowledge and a little bit of stillness at the same time. But no pressure. This isn't a race to click anything. We're not in a hurry tonight, because the cosmos certainly isn't. When we talk about limits in the universe, it's tempting to think of them as walls. The highest mountain you can climb before there's nothing but thin air, the deepest point in the ocean before the water pressure crushes any unprotected craft, the fastest speed you can reach before your vehicle gives out. But cosmic limits are different. They're not obstacles you can push through with better equipment or more determination. They are, as far as we can tell, built into the structure of reality itself. If you imagine a map of everything that's possible, these limits are the edges of the paper. Past them, the map simply stops. It's not that there's something else hidden there, at least nothing we know how to measure. It's that the there itself seems to be missing. This idea that the universe has hard boundaries is strange because for most of human history, we lived in a world where the idea of limit was always about lack of knowledge. Sail far enough across the ocean, people once thought, and you might fall off the edge. That edge turned out to be an illusion. There was more world just waiting to be found. Many of the limits humans have encountered in the past have been temporary. The sound barrier was once called a wall until faster aircraft made it routine. The depth of the Mariana Trench was unreachable until submersibles made the trip. We've been conditioned to think of limits as challenges to overcome, but when it comes to the cosmos, some of them might be absolute in a way we've never had to accept before. Take the speed of light, for example, but we'll get into that more fully later. For now, it's enough to say that this speed isn't just about how fast light travels. It's tied into how causality works, how information moves, and even how the fabric of space and time itself is shaped. Or think about temperature and the strange fact that there's a point where you can't get any hotter because the very idea of temperature stops making sense. These limits aren't just a matter of building a stronger machine or turning up the dial. They're woven into physics at the deepest levels we've explored. The fascination with these ultimate boundaries is more than curiosity. They tell us about the rules of the universe in a way that everyday measurements never can. You can learn a lot about how a system works by watching it operate normally, but sometimes the most revealing moments come when you push it to its extreme. If you want to know how strong a bridge is, you find the point at which it bends or breaks. If you want to know how far a voice carries, you shout until the sound fades. In physics, limits are like those stress points. They reveal not just what's possible, but why things are the way they are. It's worth pausing for a moment here to think about how unusual it is that such limits even exist. You could imagine a universe without them, a place where speeds could climb forever, temperatures could rise without bound, distances could shrink infinitely, and time could be sliced into ever smaller fragments without hitting a floor. But the universe we live in is full of boundaries that say, stop, long before infinity. Why that is, why there's a fastest speed, a smallest length, a shortest time, is one of the great questions that ties together everything from the largest structures in the cosmos to the tiniest quantum fluctuations. Some of these limits are ones we've tested directly, bumping up against them in experiments or observations. Others are far beyond our reach, predicted only by theory, sitting at the edges of our equations like dim lights on a distant shore. They're not just curiosities. They set the stage for every process in the universe, from the birth of stars to the evaporation of black holes. And the more we understand about them, the closer we get to understanding whether the cosmos is infinite in some directions and finite in others, or whether it's all wrapped up in a way we haven't yet imagined. When you think about the word absolute, it can feel intimidating. Absolute zero, absolute certainty, absolute vacuum. It sounds like something fixed, unyielding, and complete. In the context of cosmic limits, absolute often means we've run into the very framework that defines reality. If you want to picture it, think of the rules in a board game. You can change the pieces, you can try different strategies, you can play fast or slow. But if you try to move outside the board entirely, the game just stops making sense. Cosmic limits are like the edges of the game board. They're not optional. One of the most intriguing things about these boundaries is that they show up across wildly different scales. At one end, there are limits so small they're beyond the reach of even our most powerful microscopes. Distances and durations where the smooth picture of space and time crumbles into something grainy and unpredictable. At the other, there are limits so vast that no telescope will ever see beyond them, because light itself hasn't had time to reach us since the beginning of the universe. It's a strange symmetry, the smallest possible and the largest possible, both shaping what we can observe and understand. It's also true that some of these limits come with loopholes, or at least apparent ones. The speed of light, for example, is an unbreakable limit for anything moving through space. But space itself can expand faster than that, carrying galaxies with it. That's how we can talk about parts of the universe receding from us at speeds greater than light without breaking physics. These aren't contradictions. They're reminders that the limits are part of a larger system, and you have to understand the rules in context. Of course, knowing about these limits doesn't mean we're anywhere close to mastering them. In many cases, they remain more like signposts than destinations. We can calculate the Planck temperature, but no experiment has ever reached it, and probably never will. We can write equations for the shortest possible time, but our instruments are nowhere near precise enough to measure it directly. And yet, these ideas shape the way physicists build theories. They act as guardrails, telling us where our equations are allowed to go and where they must stop. Sometimes I wonder if part of the human attraction to these limits is the same thing that draws us to horizons. You can't see beyond them, but you can imagine what might be there. Even if you never reach it, the very fact that there's a boundary makes the space inside it feel more defined, more real. The universe might not have been designed with human curiosity in mind, but it's certainly generous with places for us to wonder about. As we move forward, we're going to explore these absolute cosmic limits one by one, not just to list them, but to understand how they work, why they exist, and what they mean for the universe we live in. We'll look at the speed limit set by light, the temperature limit set by fundamental physics, the smallest distances where our current understanding breaks down, the most extreme densities nature can achieve, the edges of what we can see, and the strange upper bounds on things like information and energy. Along the way, we'll see how each of these limits connects to the others, and how together they sketch the outline of a reality that's vast but not without its boundaries. So wherever you are, however you're listening, take a moment to settle in. We're going to start with something that might seem simple at first, the meaning of a limit when you're talking about the entire universe. When we use the word limit in everyday conversation, it usually means something negotiable. The speed limit on a road might be enforced, but you could drive faster if you really wanted to, even if it's not wise. A limit on your luggage weight can sometimes be stretched with a sympathetic check-in clerk. Even personal limits, like how much coffee you can drink before you start feeling jittery, aren't carved into stone. They can shift with mood, practice, or necessity. We're used to limits being flexible, sometimes inconvenient, sometimes arbitrary, but rarely absolute. That's why when scientists talk about limits in the universe, it's important to understand that these aren't the same kind of boundaries we deal with in daily life. They aren't suggestions or guidelines. They're not there because someone decided they should be. They seem to be there because the universe itself wouldn't work the way it does if they weren't. It's interesting to think about how the very idea of a limit shapes the way we think about reality. For much of history, people assumed that most natural limits were just temporary ignorance. There was a time when the highest speed you could travel was the speed of a galloping horse. Then came the steam train, then the automobile, then the airplane, each one making the old limit obsolete. The same with distance. Once, the horizon was the furthest point anyone could imagine reaching. Then ships crossed oceans, telescopes saw other planets, spacecraft touched the edge of the solar system, and probes sent back images from billions of kilometres away. These changes built a sense that limits are meant to be broken. We admire the people who push them, whether they're climbing the highest mountain, diving to the deepest trench, or building the fastest machine. That's why cosmic limits feel so different. They don't come from lack of technology or imagination. They come from the way the universe is built. You can try to go faster than light, but as far as physics is concerned, that's like trying to divide by zero in math. It's not just hard, it's undefined. You can try to reach absolute zero temperature, but there's no process that will get you there, no matter how clever the design. These limits are part of the structure that everything else depends on. They're like the grain in a piece of wood. You can carve along it, but you can't rearrange it without breaking the wood itself. Part of what makes these limits fascinating is that they're not always obvious. You can live your entire life without ever encountering them directly. Light moves so fast that nothing you do in daily life comes close to its speed. Absolute zero is so far below anything you'll feel outside a physics lab that it might as well be theoretical. The smallest distances and shortest times are so far beyond our senses that they only exist in the mathematics of advanced physics. And yet, even if you never meet them face to face, they're affecting the way the universe behaves around you. Your phone works because signals can't go faster than light. Stars shine the way they do because there's a maximum brightness they can reach before the pressure pushes matter away. Black holes have horizons because nothing can escape beyond a certain boundary. In physics, a limit is often more than a number. It's a signal that something changes when you get close to it. Push toward the speed of light and time itself slows down for you. Cram matter into a smaller and smaller space, and you reach a point where no known force can stop it from collapsing into a singularity. Heat something hotter and hotter, and eventually the very particles it's made of lose their identities in a haze of energy. These aren't just arbitrary stopping points. They're thresholds where the rules shift into something new, sometimes into territory where we don't yet understand what's going on. The language we use to talk about limits reflects this. In everyday life, limits are challenges, pushing the limit, testing the limit, breaking the limit. In science, when we say something is a limit, we usually mean that it's the edge of the known laws of nature. Not an obstacle in the road, but the edge of the road itself. If you step off, you're in a place where the usual rules don't apply and where our current equations might not even make sense. That's not necessarily bad. Exploring those edges has led to some of the biggest breakthroughs in physics, but it does mean you can't treat these limits as if they're just bigger versions of the ones we've passed before. Some limits are defined by our current theories, which means they're only as reliable as the theories themselves. If the theory changes, the limit might change too. For example, before Einstein, there was no reason to think there was a maximum speed for anything. Light was fast, yes, but in principle, why not faster? Then relativity came along and showed that speed isn't just about motion, it's tied to the very structure of space and time. Suddenly, the speed of light wasn't just a number, it was a fundamental property of the universe. Other limits, like the Planck length or the Planck time, come from combining the constants of nature in certain ways, even if we've never measured them directly. These are more like signposts our mathematics has put up at the far end of a road we can't travel yet. There's also the question of whether limits are truly universal. Do they apply everywhere, always, without exception? As far as we can tell, yes. The speed of light is the same in all directions and for all observers. Absolute zero is equally unreachable in any lab, on Earth or in space. The density limit for neutron stars seems to hold whether they're in our galaxy or far across the universe. But that's based on what we've observed so far, and the universe has a way of surprising us. There could be conditions somewhere that push past what we think is possible, in ways we can't yet imagine. If that happens, our definition of a limit will have to adapt. This is where it's helpful to think about limits not as walls, but as boundaries in a landscape. If you're walking in unfamiliar territory and you see a cliff edge, that's a limit. You can't go farther without falling. But if you find a bridge or a path around, suddenly the limit is somewhere else. Physics has found plenty of cliffs, but also plenty of bridges. We can't reach absolute zero, but we can get unimaginably close. We can't go faster than light, but we can use gravitational lensing or quantum entanglement to do things that bend around the spirit of the rule without breaking it. These workarounds don't erase the limit, but they show that limits can be more complex than they look at first. Even in cases where a limit seems rigid, there's often a rich structure in how you approach it. As you get close to absolute zero, matter starts to behave in ways that seem alien compared to normal temperatures. Superconductivity, superfluidity, quantum effects that dominate the behavior of entire systems. As you push toward the speed of light, relativistic effects don't just appear suddenly at the limit. They build gradually, warping your measurements of time and distance in ways that get more dramatic the closer you get. These transitional regions are often as interesting as the limits themselves, because they reveal how the universe shifts gears. It's also worth remembering that limits aren't always bad news. In some ways, they make the universe more stable and predictable. If there were no speed limit, the structure of cause and effect might break down. If there were no lowest possible temperature, strange instabilities might creep into the behavior of matter. If there were no limits on density, the universe might collapse into black holes far more easily. Limits give the cosmos a kind of scaffolding. They keep certain extremes from running away unchecked. They're part of why the universe looks and behaves the way it does, rather than turning into something unrecognizable. The way we discover these limits is often indirect. You can't measure the Planck time directly, but you can study the theories that predict it, and see if those theories match what we observe in less extreme situations. You can't travel to the edge of the observable universe, but you can measure the faint light from its most distant galaxies and see how it behaves. You can't create the hottest possible temperature, but you can push particle accelerators to higher and higher energies and look for patterns in how the results change. Each time, the limit shows itself not by being reached, but by shaping what happens as you get close. Sometimes the act of naming a limit changes the way we think about the universe. Once you say, there is a maximum speed, you can start to ask questions about what that means for travel, communication, and the structure of space and time. Once you say there is a smallest possible length, you can begin to imagine how the smooth picture of the universe we see might actually be built from something discrete and granular. These questions don't just deepen our knowledge, they redefine what we think is possible. There's also an emotional side to all this. For some people, the idea that there are hard limits in the universe feels frustrating, even claustrophobic. For others, it's comforting. Knowing that there's a fastest speed, a brightest star, a farthest horizon can make the cosmos feel more ordered, less chaotic. It's a reminder that even in its vastness, the universe has structure, and that structure is something we can understand, at least in part. As we keep exploring these ideas, it's important to carry both curiosity and humility. Curiosity because the limits we know are gateways to deeper understanding. Humility because every time we've thought we understood the full picture, new discoveries have shifted the boundaries. The universe doesn't owe us consistency in how it reveals itself. It just is, and we do our best to read the signs. If you wanted to pick a single number that quietly runs the universe from behind the scenes, it would be about 219,792,458 meters per second. That's the speed of light in a vacuum, a value so exact it's written into the very definition of the meter itself. For most people, that's just an impressive figure you might remember from a science article or a high school physics class. But in the world of fundamental physics, it's the ultimate speed limit for anything with mass or any kind of information. No matter how much energy you throw at an object, no matter how advanced your technology, you can't make it go faster than that. It's not a matter of difficulty. It's a matter of the way space-time itself is built. At first glance, it's not obvious why there should be a speed limit at all. Before Einstein came along, speed was just speed. If you were in a carriage moving at 20 kilometers per hour and you threw a ball forward at 10 kilometers per hour, someone standing on the side of the road would see the ball moving at 30 kilometers per hour relative to them. Speeds just added up. It was intuitive, and it worked fine for everyday life. Light, though, refused to play by those rules. Experiments in the late 19th century, most famously the Michelson-Morley experiment, kept showing that no matter how you moved relative to it, light's speed stayed the same. You could be moving toward it, away from it, or sideways, and it didn't matter. It still came at you at the same pace. Einstein's special relativity made sense of this odd behaviour by rewriting the relationship between space and time. In his view, the speed of light wasn't just the speed of a particular kind of wave, it was the universal speed limit baked into space-time itself. The c in the equations of relativity is a constant for everyone, everywhere, and that constancy has strange consequences. If you try to accelerate an object with mass closer and closer to that speed, you have to keep giving it more energy, and the amount of energy required grows without bound. By the time you reach the speed of light, the required energy is infinite. That's why no particle with mass can actually get there. The consequences of having such a limit are more than just nothing can go faster than light. They touch on how time passes, how distances contract, and how cause and effect work. Imagine you're in a spaceship moving at a significant fraction of light speed. To you, inside the ship, time feels normal. Your clock ticks at the usual rate, your coffee cools the same way it would at rest, your thoughts come at the same pace. But to someone watching from outside, your clock is running slow, your coffee is cooling slowly, and you're aging more slowly than they are. This effect, called time dilation, is small at everyday speeds but becomes dramatic as you get close to light speed. It's been measured directly with high-precision atomic clocks on fast-moving aircraft and satellites. Distance behaves strangely too. From your perspective on the ship, as you go faster, the distances in the direction of your motion actually shrink. A trip to a star that would take decades at ordinary speeds might seem much shorter for you if you could travel close to light speed. This isn't just an optical illusion, it's built into the geometry of space-time, and it ensures that the speed of light is the same for all observers no matter how they move. What's easy to overlook is that this limit isn't just about light. Light just happens to be the thing we encounter most often that moves at the maximum speed. The real rule is that nothing can carry information faster than this speed. That includes gravitational waves, which ripple through space-time itself, and any other kind of signal or force. This limit is why there's an observable universe at all. There's a maximum distance from which light could have reached us since the beginning of the cosmos, and beyond that, we simply can't see. It's why distant events, no matter how dramatic, can't affect us instantly. Even the sun, a mere 8 light minutes away, could vanish, and we wouldn't know for those 8 minutes. The idea of a cosmic speed limit has been tested in countless ways, and so far it's held up. We've accelerated particles in colliders to more than 99.999% of light speed, and while they gain huge amounts of energy, they never break through the limit. High-energy cosmic rays from deep space, some of the fastest particles nature produces, slam into our atmosphere moving at nearly light speed, and they too respect the boundary. If there's a loophole, we haven't found it. That hasn't stopped people from wondering about ways around it. Science fiction is full of faster-than-light travel, warp drives, hyperspace jumps, wormholes, because the alternative is that interstellar travel takes a very, very long time. In real physics, some ideas have been proposed that might let you get around the speed limit without technically breaking it. One is the concept of a warp bubble, where you compress space in front of your ship and expand it behind, moving the bubble itself faster than light relative to the outside universe, while staying still inside it. The mathematics of general relativity allow for this in principle, but the amount and type of energy needed are beyond anything we know how to produce, involving something called negative energy that has never been observed in usable quantities. Another apparent loophole is that space itself can expand faster than light. During the early universe's inflationary period, space expanded so rapidly that regions were pushed out of causal contact with each other in fractions of a second. Even now, distant galaxies in the far reaches of the universe are receding from us faster than light due to the expansion of space. This doesn't violate the speed limit because nothing is moving through space faster than light. The fabric of space itself is stretching. Quantum physics brings its own curiosities. Quantum entanglement creates correlations between particles that seem to happen instantly, no matter how far apart they are. Measure one particle here, and the other knows about it immediately. But as strange as that sounds, it can't be used to send information faster than light. The results are random until compared later, and that comparison still requires ordinary communication bound by the same limit. You might ask why the universe should have such a limit in the first place. The simplest answer is that it keeps the laws of physics consistent for all observers. Without a universal speed, different observers moving relative to each other would measure different laws, and the structure of cause and effect could break down. The speed of light as a constant ensures that the order of events makes sense, and that the same physical principles apply no matter where or how you move. One of the most fascinating things about this limit is how deeply it's connected to the nature of space-time itself. In Einstein's formulation, space-time is a four-dimensional fabric, where events are located in both space and time coordinates. The speed of light is the slope that separates what can influence what. The dividing line between inside and outside a given event's light cone. Anything inside the cone could be connected by a signal or a physical influence. Anything outside is forever out of reach. The practical consequences of this are everywhere, even if you never notice them. GPS satellites, for example, have to account for both the slower ticking of their onboard clocks due to their speed relative to Earth, and the faster ticking due to being farther from Earth's gravity. Both effects are predicted by relativity, and both depend on the universal speed limit. Without these corrections, your phone's location could be off by kilometers within minutes. In astrophysics, the speed limit plays a role in shaping how stars live and die. When massive stars explode as supernovae, the shockwaves and light they emit still take time to cross space. The events we see through telescopes often happened millions or billions of years ago, their signals only now arriving. Even within galaxies, the time it takes light to cross vast distances means that now is a local concept. In a sense, the universe is full of different nows, each defined by the light travel time between places. Thinking about the speed of a light as a limit can be both humbling and inspiring. It reminds us that there are real boundaries on how quickly we can reach out into the universe, but it also gives us a precise framework for understanding that universe. It shapes not just what we can do, but how we think about space, time, and causality. And while it might feel like an obstacle to dreams of instant exploration, it's also a constant companion in every signal, every beam of light, every glance at the stars. If you want to see the universe casually flexing against its own speed limit, you don't have to look at spaceships or science fiction. You just have to pay attention to the sky. Not the calm, starlit version you see at night, but the invisible rain of high-energy particles that is constantly arriving here on Earth. These particles, known as cosmic rays, have been falling on our planet for as long as there has been a planet to hit, and some of them are moving so close to the speed of light that they push right up against the ultimate barrier we talked about before. They're not theoretical, they're here, right now, streaking through the atmosphere, and some of them are more extreme than anything we can make in a lab. The term cosmic ray might sound like a beam of light or radiation, but that's not quite right. Most cosmic rays are actually atomic nuclei, often just protons but sometimes heavier elements, that have been accelerated to incredible energies somewhere out in space. They can come from a wide range of sources: the sun, exploding stars, distant galaxies, maybe even processes we don't fully understand yet. When they collide with atoms in Earth's atmosphere, they create showers of secondary particles, many of which make it all the way to the ground. You've probably been hit by cosmic rays many times without ever noticing. Most cosmic rays are relatively tame as cosmic phenomena go. The sun produces plenty during solar storms, and they can affect satellites, astronauts, and even power grids on Earth. But there's another class of cosmic rays that's far more mysterious: ultra-high-energy cosmic rays. These are particles so energetic that they make the output of our most powerful accelerators look like a dim flashlight compared to the sun. The most energetic ever detected, recorded by the Fly's Eye detector in Utah in 1991, carried an energy equivalent to a well-thrown baseball, packed into a single proton. In the particle physics world, that's an almost absurd number. To get a sense of scale, the Large Hadron Collider accelerates protons to about 7 tera-electron-volts, TeV, of energy. The Oh My God particle, as the 1991 one came to be called, had around 300 million TeV. That's not just impressive, it's puzzling. Accelerating something to that energy is no small feat, even for nature. We have theories about how such particles might get going: shock waves from supernova remnants, the violent environments near supermassive black holes, collisions of galaxy clusters. But the truth is, we still don't have a complete explanation. The farther you want to accelerate a charged particle, the more powerful and extended your accelerator has to be. For cosmic rays at these energies, the accelerator would have to be on the scale of entire galaxies, or even larger. Whatever is doing it, it's far beyond anything we could build. Even more curious is how these particles make it to Earth at all. Space is not empty. There's a thin fog of low-energy photons from the cosmic microwave background, the leftover radiation from the Big Bang filling the universe. At ultra-high energies, protons colliding with these photons should lose energy quickly, a process predicted in the 1960s and called the Greisen-Satzepin-Kuzmin, or GZK, cutoff. This limit suggests that particles with energies above a certain threshold, about 50 million TeV, should only be able to travel tens of millions of light years before being slowed down. Yet we've detected cosmic rays above this limit, which means either they're coming from relatively nearby sources, or something about our understanding of their interactions needs adjusting. When an ultra-high energy cosmic ray does reach us, it doesn't arrive quietly. It slams into molecules high in the atmosphere and triggers a cascade of secondary particles called an air shower. This shower can spread over many kilometers by the time it reaches the ground. Some of those particles are muons, cousins of the electron that can penetrate deep into matter. That means that right now, as you listen to this, muons from cosmic ray showers are passing through you. They're harmless in the tiny doses we receive, but they're a reminder that the universe is constantly brushing up against us, even when we're not aware of it. Detecting these events takes patience and scale. Facilities like the Pierre Auger Observatory in Argentina use an array of detectors spread across thousands of square kilometers, along with telescopes that can watch the faint glow of nitrogen in the atmosphere when these showers occur at night. Over years of observation, scientists build up a picture of where the most energetic particles are coming from, what they might be made of, and how often they arrive. Patterns in their arrival directions could hint at their sources, though magnetic fields in space tend to scramble their paths, making it hard to trace them back directly. What's fascinating is that these particles, as close as they are to the speed of light, show us just how the speed limit works in practice. Even moving at 99.99999% of the light speed, they still take measurable amounts of time to cross space. If one of these particles came from a galaxy 100 million light-years away, it's been travelling for almost exactly that long to get here. In its own frame of reference, thanks to time dilation, the journey might feel much shorter, perhaps only minutes or hours. But to us, the wait is immense. This also means that when we detect one, we're detecting a messenger from the distant past. The universe looked very different when some of these particles began their journey. Stars were younger, galaxies were in different positions, and entire cosmic structures may have shifted. Yet here they are, arriving in the thin air high above us, announcing their presence in the brief flashes of light and particle bursts they leave behind. In a way, cosmic rays are nature's own high-energy experiments. In laboratories like the Large Hadron Collider, we can control the conditions, tune the energies, and analyse the results in exquisite detail. But we're limited by the size of the machines we can build and the energy we can feed them. The universe has no such limits, at least not in terms of engineering. It uses magnetic fields, shock fronts, and gravitational monsters to fling particles to energies we can barely imagine. By studying these naturally occurring accelerators, we might learn about physics at energies far beyond what we can test directly. There's a possibility that ultra-high energy cosmic rays could even hint at new physics. If some of them are able to skirt the GZK cutoff, perhaps they're not protons at all but other more exotic particles. Or maybe the way they interact with the cosmic microwave background isn't quite what we think. Each detection is a clue, but because they're so rare, the highest energy ones might only hit a given square kilometre of Earth once every few centuries. Building up a solid picture takes decades. The sheer rarity of these particles adds to their mystique. Imagine waiting for a raindrop in a desert, and when it finally falls, it carries the history of an ancient storm from the other side of the world. That's what it's like to catch one of these ultra-energetic cosmic rays. The equipment sits and waits, often in remote locations far from city lights, watching the sky for the faint traces they leave behind. Most of the time, what it sees is ordinary, the steady drizzle of lower energy particles from the sun and other sources. But every now and then something extraordinary streaks through, and the data logs record a particle that's been travelling almost as fast as the universe allows. And even though they're so elusive, they're not just a curiosity. These particles interact with the atmosphere in ways that can affect its chemistry, contribute to the background radiation at Earth's surface, and provide natural laboratories for studying fundamental forces. They've helped confirm predictions of relativity and particle physics, and they continue to challenge our understanding of where the universe's most extreme environments might be hiding. It's almost funny to think that the fastest things we've ever observed directly are not sleek spacecraft or engineered machines, but single atomic nuclei hurled across unimaginable distances by forces we still can't fully pin down. They don't need crew quarters or navigation systems. They don't even need to aim well, because the vastness of space means they can wander for millions of years before happening to cross paths with our tiny planet. And when they do, they remind us that the speed limit we talked about before isn't just an abstract idea. It's a boundary that the universe constantly brushes against, testing it, but never crossing it. From these fastest particles, it's a short leap to thinking about other extremes, not in speed this time, but in temperature. Because just as there's a ceiling on how fast anything can move, there's also a ceiling on how hot anything can get, a limit that sits so far beyond anything we've ever created that it belongs to the earliest instance of the universe itself. When you hear about the hottest anything, it's usually in the context of something we can see, touch, or at least imagine. The surface of the sun, for example, at about 500 degrees Celsius, is already far beyond what any human could survive. The core of the Sun, at around 15 million degrees Celsius, is hotter still, enough to fuse hydrogen into helium and power the star for billions of years. We've measured even more extreme environments in the universe. The inner regions of supernova explosions, where temperatures can spike to billions of degrees, or the plasma near black holes, where matter spirals in and releases staggering amounts of energy before disappearing past the event horizon. But all of these pale in comparison to something called the Planck temperature. This is not just hot in the way we usually mean it. It's the theoretical maximum temperature the universe can have, about 1.4168 aurora TX, 32 Kelvin. That's a 1 followed by 32 zeros. To put it in perspective, if you somehow took every atom in the universe and gave it the kind of energy implied by this temperature, the laws of physics as we currently understand them would break down entirely. It's not that things would simply melt or vaporize. Those words stop making sense here. At the Planck temperature, the very structure of space-time itself would be overwhelmed. Temperature, at its core, is a measure of the average energy of the particles in a system. The hotter something is, the faster its particles move. In solids, atoms vibrate in place. In liquids and gases, they zip around more freely. Increase the temperature and those movements get more and more energetic. But there's no such thing as faster than light motion for these particles, so at first glance you might think there'd be a natural speed-related limit on temperature. The story's a bit more subtle than that. As particles move faster and faster, their kinetic energy grows, and once you're dealing with relativistic speeds, meaning speeds close to the speed of light, adding more energy doesn't just make them move faster, it starts going into their mass energy, warping the conditions they're in. The Planck temperature is reached not because the particles themselves hit some velocity barrier, but because beyond this point, the energy density is so great that it would create black holes at subatomic scales. If you tried to confine that much energy into any region of space, gravity would become as strong as the other fundamental forces, and the neat separation of physics into quantum and gravitational regimes would vanish. This is where our equations simply stop giving reliable answers. At temperatures approaching this limit, quantum effects of gravity, something we don't yet have a complete theory for, would dominate. The neat fabric of space-time, which general relativity describes so well at lower energies, would become turbulent, foamy, perhaps even discontinuous at scales as small as the Planck length. It's worth noting that this isn't a limit you can approach gradually in the same way you can, say, approach absolute zero from above. Absolute zero is a lower bound on temperature, one you can get closer and closer to with clever cooling techniques, though never quite reach. The Planck temperature is an upper bound that, as far as we know, has only ever been reached once in the history of the universe, in the first tiny fraction of a second after the Big Bang. Back then, the entire cosmos was compressed into a volume so small and dense that the temperature was right at or near the Planck scale. In that state, the four fundamental forces we know today, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, may have been unified into a single force. From that unimaginably hot beginning, the universe expanded and cooled. Within a tiny fraction of a second, temperatures dropped enough for gravity to separate from the other forces, and then further cooling allowed matter as we know it to start forming. That means everything you see today, from galaxies to your own body, is built from material that once existed in that searing unified state. The Planck temperature is like the ultimate reset point, the condition from which the universe emerged, and the one that no known process in today's cooler, more spread out cosmos can recreate in full. We've come close, in a relative sense, in particle accelerators. At facilities like the Large Hadron Collider, collisions between particles can produce temperatures in the trillions of degrees, briefly hotter than the core of a supernova, hot enough to melt protons and neutrons into a soup of quarks and gluons called quark-gluon plasma. These experiments are windows into the first microseconds after the Big Bang, but they are still laughably far from the Planck temperature. there's a gap of about 20 orders of magnitude between what we can produce and the theoretical maximum. That's not a small gap you might close with a few technological breakthroughs. It's a chasm so wide that crossing it would require energies and densities far beyond anything in our current reach. Interestingly, there's no law of physics that says the Planck temperature is inherently impossible in the same sense that faster-than-light travel is. It's just that the conditions needed to reach it would destroy the very framework in which our physics operates. If you tried to pump that much energy into a system, it wouldn't just get hotter, it would collapse into a black hole or cause such extreme space-time distortions that our existing concepts of temperature, space and time would stop being meaningful. This is why some physicists talk about it less as a temperature and more as a threshold, the point beyond which you need a new theory of quantum gravity to even describe what's happening. The Planck temperature also appears naturally when you combine certain constants of nature: the speed of light, Planck's constant, and the gravitational constant. It's not something we measure directly and then named. It's a number that falls out of the math when you ask, what happens when the scales of quantum mechanics and general relativity meet? In that sense, it's not just about heat. It's a statement about the deepest structure of the universe. It's one of those limits that isn't arbitrary, but emerges from the relationships between the most fundamental things we know. Thinking about it raises questions about the nature of temperature itself. We think of temperature as an emergent property, the collective behaviour of many particles. But at the Planck scale, when space-time itself is fluctuating violently, and particles as we know them might not even exist in a recognisable form, does temperature even make sense? Or is it just a convenient label we apply in the realm where our current physics still works? These are open questions, and they're part of why physicists are so interested in finding a theory that unifies quantum mechanics with gravity. In astrophysics, you sometimes see temperatures approaching fractions of the Planck value in thought experiments about extreme objects. Imagine matter falling into a black hole so fast that the shock heating near the event horizon sends it into a frenzy of particle creation and annihilation. Or collisions between ultra-high energy cosmic rays, where the energies involved are staggering but still far below the Planck level. Even in these extreme scenarios, nature seems to keep a wide margin before hitting the ceiling. It's also intriguing to think about what too hot means in a cosmic sense. In everyday life, being too hot means damage to biological systems, melting, burning, destruction. At the Planck temperature, too hot means the breakdown of space-time itself. You can't really burn or melt space-time. You can only push it to the point where it's no longer smooth, where quantum uncertainty becomes so extreme that distances, times, and even causal order become ill-defined. That's why physicists treat this temperature not as just another extreme, but as a marker for the edge of our understanding. While it's far beyond anything we can approach experimentally, the Planck temperature isn't just an abstract curiosity. It plays a role in theoretical work on the early universe, on black hole evaporation, and on the limits of information storage and processing in physical systems. In some speculative models, the physics at this temperature could involve exotic states of matter, new dimensions, or entirely different kinds of particles. Until we have a theory of quantum gravity, these ideas remain speculative, but they're anchored in the recognition that this is a meaningful boundary in the landscape of possible conditions. In a way, the Planck temperature mirrors the speed of light as a limit. Both are not just physical measurements, but constants that shape the structure of reality. The speed of light is the fastest anything can move through space. The Planck temperature is the hottest anything can be, before space itself stops behaving in the way we understand. They're both thresholds written into the equations of physics, and neither is something you can break without leaving the realm of the known. If the Planck temperature is a kind of upper boundary where heat becomes so intense that the structure of space-time itself would buckle, then absolute zero is its mirror image on the opposite end, the theoretical point where heat vanishes completely. It's a boundary that's been known to science for much longer. one that feels more intuitive because we can imagine things getting colder and colder, motion slowing, energy draining away. But this boundary has its own peculiar twist. Just like the Planck temperature, it's not something you can actually reach no matter how carefully you try. Absolute zero sits at exactly 0 Kelvin, or 273.15 degrees Celsius, or 459.67 degrees Fahrenheit. Those numbers aren't just for trivia. They mark the point at which the classical picture of particles moving due to heat reaches its logical end. Temperature, in its simplest form, is a measure of the average kinetic energy of the particles in a substance. Warm objects have particles jostling vigorously. Cool objects have particles moving more slowly. Cool them far enough, and those motions slow to an almost imperceptible crawl. At absolute zero, in classical physics, you'd expect all motion to stop entirely. But quantum mechanics changes that story. It tells us that particles can never be completely still. Even at absolute zero, there remains what's called zero-point energy, the lowest possible energy a quantum system can have. This is a direct consequence of the Heisenberg uncertainty principle, which says you can't know both the exact position and momentum of a particle at the same time. If a particle were completely motionless, you'd know both, and that's forbidden. So even at the coldest temperature nature allows, particles still have a faint quantum hum, a jitter that keeps the universe from ever being truly frozen. In practical terms, absolute zero is unreachable, because every time you try to remove the last traces of heat from a system, the very methods you use, laser cooling, evaporative cooling, magnetic traps, involve interacting with the particles, and that interaction adds a tiny bit of energy back in. The closer you get, the harder it becomes to make any further progress. Cooling something from room temperature to a few kelvins above absolute zero is relatively straightforward in physics labs. Going from a fraction of a Kelvin to an even smaller fraction requires extraordinary precision and isolation from any source of heat, even the faint warmth of surrounding equipment or the photons in the room. Despite these challenges, scientists have gotten astonishingly close. In some experiments with dilute gases of atoms, temperatures as low as a few billionths of a Kelvin have been achieved. At those extremes, matter behaves in ways you never see at higher temperatures. One famous example is the Bose-Einstein condensate, a state of matter predicted in the 1920s by Satyendranath Bose and Albert Einstein, and first created in a lab in 1995. In a Bose-Einstein condensate, a group of atoms is cooled so close to absolute zero that they all collapse into the same quantum state, effectively behaving like a single superatom with shared properties. In this state, quantum effects that are normally only visible at microscopic scales become evident at macroscopic scales, as if the atoms are moving in perfect unison. Getting to such low temperatures requires a multi-step process. First, the sample is cooled using techniques like laser cooling, where carefully tuned beams of light are used to slow the atom's motion. It sounds counterintuitive. Light, which we usually think of as heating things, can be used to cool them by making the photon's momentum oppose the atom's movement. After this, other methods like evaporative cooling take over, removing the highest energy atoms from the system so that the average energy, and thus the temperature, drops further. These experiments aren't just academic exercises. Understanding matter at extremely low temperatures has led to advances in precision measurements, superconductivity, and quantum computing. In superconductors, for example, cooling certain materials below a critical temperature allows electrons to move through them without any electrical resistance. In superfluids, another low-temperature phenomenon, liquids can flow without viscosity, creeping up the sides of containers or flowing endlessly in loops without losing energy. Absolute zero also plays a role in defining other physical limits. The third law of thermodynamics states that as you approach absolute zero, the entropy, a measure of disorder, of a perfect crystal approaches zero as well. This ties the coldest possible temperature to the most ordered possible state of matter. But just as the first and second laws of thermodynamics are unbreakable, so too is this one. You can get arbitrarily close to perfect order, but never quite arrive. What's remarkable is how different the behaviour of matter becomes when you get close to this limit. At everyday temperatures, thermal motion dominates. Particles are bumping into each other, vibrating and exchanging energy constantly. Near absolute zero, those motions nearly vanish, and quantum effects start to govern the scene. Waves of probability replace definite positions and velocities. Instead of particles behaving like billiard balls, they act more like overlapping clouds, their identities sometimes merging in ways that defy our everyday intuitions. And while we think of extreme cold as something rare and laboratory-bound here on Earth, it's actually common in the cosmos. The space between stars and galaxies is only a few degrees above absolute zero, cooled by the expansion of the universe over billions of years. The cosmic microwave background, the faint glow left over from the Big Bang, has a temperature of about 2.7 kelvins, making intergalactic space colder than any natural place on our planet. Certain nebulae and shadowed craters on the Moon, shielded from sunlight for millions of years, have been measured at even lower temperatures close to that cosmic background. In a sense, the universe is always moving toward this limit. Stars burn through their fuel and eventually go dark. Matter spreads out, and energy becomes more evenly distributed. Given enough time, far more than the current age of the universe, even black holes will evaporate through Hawking radiation, and what's left will be a thin soup of particles at a temperature barely above absolute zero. This far future state, sometimes called the heat death of the universe, isn't a cold in the way we normally feel it. It's the end of useful energy, a point where no process can occur that would sustain structure, complexity, or life. The coldest possible temperature, then, is not just a laboratory curiosity. It's the universe's quiet end point, the flip side of the fiery chaos near the Planck temperature at the very beginning. The beginning was heat beyond heat. The end, if it comes, will be cold beyond cold. And just as the Planck temperature marked the breakdown of our understanding of space-time, absolute zero marks the breakdown of many of our everyday intuitions about matter, motion, and energy. From the realm of extreme cold, it's a natural step to think about the smallest possible things, not in temperature, but in distance. Because just as there's a limit to heat and cold, there may be a limit to how finely you can slice space itself, a smallest possible scale beyond which the very concept of distance stops making sense. If you've ever looked closely at something, really closely, it's tempting to imagine that you could just keep zooming in forever. A photograph of a leaf reveals veins, the veins show cells, the cells show organelles, and so on, all the way down to molecules and atoms. And with the right tools like powerful electron microscopes or particle accelerators, we really can peer far beyond what the naked eye can see. But eventually you reach a strange question. Is there such a thing as the smallest possible distance? Is there a point where zooming in stops being meaningful, because space itself is no longer the smooth, continuous backdrop we think it is? This idea takes us to something called the Planck length. At roughly 1.616 x 10 to 35 metres, it's about 100 million trillion times smaller than the diameter of a proton. It's a scale so far removed from everyday experience that it's almost impossible to visualise. If an atom were the size of the observable universe, the Planck length would be roughly the size of a tree in that universe. In other words, it's absurdly, mind-bendingly small. The Planck length isn't just a number plucked from thin air. Like the Planck temperature we talked about earlier, it falls out of combining three of nature's most fundamental constants: the speed of light, c, Planck's constant, h, and the gravitational constant, g. Put together in a particular way, they give you a length scale at which the effects of both quantum mechanics and general relativity are equally important. At larger scales, you can often get away with using one theory or the other: quantum mechanics for the tiny, relativity for the massive. But at the Planck scale, neither works on its own. and our current physics doesn't yet have the unified framework needed to describe what's going on. In the world we're familiar with, space seems continuous. You can draw a line and divide it in half, then divide that half in half again, and keep going as long as you like. That's how classical geometry works, and it matches our everyday sense of how distances behave. But at the Planck length, that picture may no longer hold. Many physicists suspect that space at this scale isn't smooth, but instead is quantized, made up of discrete units, like pixels in a digital image. If that's true, then the Planck length might represent the size of those fundamental pixels of space-time, the smallest chunks out of which reality is built. Why should there be such a smallest distance? One reason comes from thinking about how much energy you need to probe a small scale. To see something tiny, you have to use particles or waves with a very short wavelength. In quantum mechanics, shorter wavelengths mean higher energies. Push this logic far enough, and at some point the energy you concentrate into a tiny region will be so great that it collapses into a black hole. That happens right around the Planck length. This means that if you tried to measure anything smaller than that, you just end up creating a black hole instead of getting more detail. Nature seems to have built in a hard stop on how far you can push your measuring stick. Another reason the Planck length comes up is in speculative theories of quantum gravity. The as yet unfinished effort to merge quantum mechanics with general relativity. Some approaches, like loop quantum gravity, explicitly predict that space is made of finite loops of area and volume, with the Planck scale setting the size of the smallest possible loop. Others, like certain interpretations of string theory, suggest that strings themselves are roughly this length, making it impossible to probe anything smaller because there simply isn't a smaller in the theory. It's worth noting that the Planck length isn't something we've ever measured directly, and probably never will, at least not in the near future. The energy is required to resolve structures that small are far beyond anything we can generate. Even our most ambitious particle accelerators are hopelessly underpowered for the task. The gap between what we can do and what we'd need is almost unimaginably large. So for now, the Planck length lives in the realm of theory, a feature of the mathematical landscape that we haven't been able to test in the lab. Still, it's not purely hypothetical. The fact that it emerges naturally from combining constants we've measured very precisely suggests it's telling us something real about the structure of the universe. And while we can't directly explore it, we can look for indirect hints. For example, some ideas in quantum gravity suggest that over vast cosmic distances, the graininess of space-time might slightly blur or delay the arrival times of very high-energy photons from distant sources like gamma-ray bursts. Observations of such events are already being used to place constraints on possible Planck scale effects. If space really does have a smallest unit, it would force us to rethink some deeply held assumptions. In a truly continuous space, motion is smooth, paths are infinitely divisible, and physical quantities like position can take on any value. In a quantized space, there's a built-in grid, and motion would be more like hopping from one point to another than sliding along a continuous track. That might sound strange, but we've already seen something similar in the quantum world. Energy levels in atoms are quantized, meaning electrons can only occupy certain allowed orbits. If space itself is quantized, then the Planck length would be the ruler marking those allowed positions. There's also the philosophical question of what it means to talk about distance at all if you can't go smaller than a certain scale. In our everyday world, the concept of here and there depends on the assumption that we can define points in space with arbitrary precision. If there's a smallest distance, those definitions would have to change. Here would really mean within this fundamental chunk of space-time, and there would mean in a different chunk. Some physicists think the Planck length might also be tied to the idea of the holographic principle. The notion that the amount of information you can store in a region of space is proportional not to its volume, but to the area of its boundary. If there's a smallest possible length, it would mean there's a smallest possible area, and that in turn would limit how much information the universe can contain in a given region. This connects the tinier scales of space to big picture concepts about entropy, black holes, and the nature of reality itself. For now, the Planck length sits in a strange position in science. It's a hard limit in the sense that our current theories tell us we can't meaningfully talk about smaller distances, but it's also a gateway, a point at which we expect the known laws of physics to give way to something new. It's not like the speed of light, which we've tested countless times and confirmed as a limit in every case. It's more like a signpost in a part of the map we haven't reached yet, telling us, beyond here, your current tools won't work. And if there's a smallest length, it makes sense to ask whether there's also a smallest possible duration, the shortest conceivable tick of the cosmic clock. Just as space might be quantized, time might also come in discrete units, with the Planck time representing the shortest interval that can exist. Understanding that boundary takes us from the question of how small can space be to how short can a moment be, and like the Planck length, it pushes us right to the edge of what physics can currently describe. When you think about time in your daily life, it tends to come in units you can measure easily: seconds, minutes, hours. If you need more precision, you can talk about milliseconds or microseconds. Technology pushes it further. Atomic clocks can measure nanoseconds and picoseconds with astonishing accuracy. But in physics, there's always the question of whether these divisions are just human convenience, or whether there's a fundamental limit built into the universe. If space might have a smallest unit, as the Planck length suggests, does time have one too? The answer, as far as our current theories tell us, is yes, at least in the sense that there's a scale below which the very concept of before and after may stop making sense. That scale is called the Planck time. It's about 539.1044 seconds. Written out in full, that's a decimal point followed by 43 zeros and then a 5. It's the amount of time it would take light, travelling at its maximum possible speed, to cross one Planck length in a vacuum. That's no coincidence. The Planck length and Planck time are tied together by the speed of light, because in relativity, distance and time are just two sides of the same space-time coin. If you think about what this means, it's staggering. A single second, something so short that you can barely clap your hands that quickly, contains about 1043 Planck times. That's 10 million trillion ticks of this most fundamental clock. At our scale, it's impossible to imagine anything happening in such a small slice of time. Even the fastest processes we've measured in particle physics, interactions between subatomic particles at high energies, take billions of times longer than this. The Planck time comes from the same logic as the Planck length. It's the point where quantum mechanics and general relativity are equally important, where you can't ignore either one. Below this scale, space-time might not behave as a smooth, continuous fabric. Instead, it could be subject to quantum fluctuations so violent that talking about a definite sequence of events, this happened, then that happened, loses meaning. Time could become foamy, with causality itself blurred. Our current theories simply don't work at this scale. In quantum mechanics, time is usually treated as a smooth parameter, something that flows uniformly against which you can measure changes. In general relativity, time is intertwined with space, bending and stretching depending on gravity and motion. But at the Planck time, those descriptions collide. We'd need a theory of quantum gravity to go further, and while there are candidate frameworks like loop quantum gravity and string theory, none have been experimentally confirmed. Why should there be such a limit on time? One way to think about it is through the uncertainty principle. To measure a very small interval of time, you'd need very high energy photons, because short wavelengths mean short periods. But at the Planck time, the energy you'd have to concentrate in such a short interval would be so enormous that it would collapse into a microscopic black hole. In other words, trying to probe a smaller tick of time would destroy the region you are measuring. The limit isn't just a quirk of math. It's enforced by the basic structure of space-time and energy. In cosmology, the Planck time marks a kind of horizon. The Big Bang Theory works backward from the universe we see today, using physics we know, until it hits this boundary at around 10:43 seconds after the beginning. Before that, our equations give nonsense. We can't say what happened earlier in any conventional sense because the concepts of earlier and later may not apply. Some cosmological models suggest that at the Planck time, the universe was a seething quantum gravitational soup, with space-time emerging only after that moment. Others suggest that time itself might be emergent, appearing from more fundamental relationships between events. It's not just an abstract boundary. The Planck time is intimately connected to the universe's earliest history. From this first tick onward, the universe expanded and cooled. Gravity separated from the other forces, and the seeds of all the structure we see today were set. In a sense, the Planck time is the universe's frame zero, the starting point for everything we can meaningfully talk about with our current science. Of course, this doesn't mean that there's some kind of cosmic stopwatch literally ticking at Planck intervals. In fact, it's not clear that time is fundamentally discrete at all. That's still an open question. Some interpretations of quantum gravity suggest that space-time is continuous, but there's simply no meaningful way to measure or define intervals shorter than the Planck time. Others suggest that time really is quantized, like the energy levels in an atom, and that the Planck time is the length of one frame in the film reel of reality. If time is quantized, it would be a profound shift in how we understand motion, change, and causality. Right now, the equations of physics treat time as something that can be divided indefinitely, even if in practice we can't measure arbitrarily small intervals. A quantized time would mean that between one moment and the next, nothing happens. There are just discrete updates to the state of the universe. But these updates would be so unimaginably fast that to us, the flow of time would still feel smooth. Even if time isn't fundamentally discrete, the Planck time still tells us something crucial. There's a limit to how far into the past or future we can meaningfully zoom. Just as you can't talk about distances smaller than the Planck length in any physical sense, you can't talk about intervals shorter than the Planck time without leaving the territory where physics as we know it applies. In both cases, the limit is telling us that our current picture of space-time is incomplete. There's a symmetry here that's worth appreciating. The Planck length and Planck time are like coordinates for the smallest possible events in the universe, the tiniest here and the tiniest now. They're not just random constants, they're part of the scaffolding that holds up our whole understanding of reality. And while we may never be able to observe them directly, they give us a boundary to aim at, a place where new physics must be waiting. Thinking about the smallest possible tick of time naturally leads to thinking about what happens when matter is pushed to its densest possible state. Because just as there's a lower bound on how small space and time can get, there's also a point where matter itself can't be compressed any further without collapsing into something even stranger. When we think about matter in our everyday lives, it's almost always in forms that are mostly empty space. The chair you're sitting on, the air you're breathing, your own body, the atoms making them up are tiny nuclei surrounded by vast regions where there's nothing but the probabilistic haze of electrons. If you scaled up an atom so that its nucleus was the size of a marble, the electrons would be orbiting at distances of tens or hundreds of meters away, and everything in between would be empty. That's why most matter feels solid, not because it's tightly packed, but because the electromagnetic forces between atoms resist compression. This makes it all the more startling to realize that there are conditions in the universe where matter is packed so tightly that those empty spaces vanish. At that point, the very structure of atoms collapses, and particles are squeezed together into forms so dense that a single teaspoon would weigh billions of tons. The most famous examples of this are neutron stars, the remnants left behind after massive stars explode in supernovae. A neutron star is essentially the collapsed core of a massive star, one that started its life many times heavier than the Sun. When such a star exhausts its nuclear fuel, the delicate balance between outward pressure from fusion an inward pull from gravity tips violently in favour of gravity. The core implodes, and the outer layers are blasted away in a spectacular supernova explosion. What's left behind is an object with a mass greater than the Sun, but compressed into a sphere only about 20 kilometres across. The gravitational pressure is so intense that electrons and protons in the atoms of the star's matter are forced to merge, creating a sea of neutrons, hence the name. Neutrons, unlike protons and electrons in ordinary matter, can sit much closer together because they're not repelled by electric charge. But they're still subject to quantum rules, specifically the Pauli exclusion principle, which says that no two fermions, the class of particles that includes neutrons, can occupy the exact same quantum state. This creates a kind of degeneracy pressure that resists further compression. That's what holds up a neutron star against gravity, at least until a certain limit. That limit is called the Tolman-Oppenheimer-Volkoff limit, and it's the neutron star's version of the Chandrasekhar limit for white dwarfs. Above a mass of roughly 2 to 3 suns, even neutron degeneracy pressure can't withstand the pull of gravity, and the star collapses into a black hole. Below that limit, the neutron star remains stable, often for billions of years, spinning rapidly and sometimes emitting beams of radiation like a cosmic lighthouse. These spinning neutron stars are known as pulsars, and they're among the most precise natural clocks in the universe. The density of a neutron star is almost beyond comprehension. Imagine taking the mass of Mount Everest and compressing it into something the size of a sugar cube. That's the kind of density we're talking about, on the order of 1017 kilograms per cubic metre. It's so extreme that if you could somehow bring a piece of neutron star material to Earth, it would fall straight through the ground, tearing a hole through the planet. Not that this could ever happen in practice. The moment that material left the crushing gravitational field of the neutron star, it would explode violently, unable to hold itself together in ordinary conditions. Inside a neutron star, the physics becomes exotic. The outer layers are thought to be a crust of nuclei packed tightly together, embedded in a sea of electrons. Beneath that, as you go deeper, the pressure becomes so intense that neutrons start to drip out of nuclei, creating a superfluid of neutrons that flows without friction. Deeper still, some models predict that the neutrons themselves may break down into their constituent quarks, forming what's called quark matter, an even denser and stranger state. If this happens, you might end up with a quark star, though whether such objects exist is still a matter of speculation. The study of neutron stars isn't just about cataloguing exotic objects. They're natural laboratories for physics under conditions we could never replicate on Earth. The combination of extreme density, intense gravity, and rapid rotation produces phenomena that contest the limits of general relativity, nuclear physics, and even theories about dark matter. For example, the collisions of neutron stars detected through gravitational waves for the first time in 2017 produce not only ripples in space-time but also huge bursts of electromagnetic radiation. These collisions are thought to be the source of many of the heavy elements in the universe, such as gold and platinum, created in the intense neutron-rich environment during the merger. In terms of density, neutron stars represent a kind of upper bound for matter that still exists as matter in any recognizable sense. Beyond that, you cross into the territory of black holes, where gravity overwhelms every form of pressure and matter collapses into a singularity, a point where, according to general relativity, density becomes infinite. Of course, we don't actually know if singularities in the mathematical sense exist in reality, or if quantum gravity effects smooth them out into something else. But either way, once you pass the neutron star limit, there's no stable form of matter left. You've gone beyond the densest matter allowed. It's worth noting that while neutron stars are incredibly dense, they're not the only place in the universe where matter approaches such extremes. The centres of atomic nuclei, for instance, have densities similar to those in neutron star interiors. About 2.3 is 1017 kilograms per cubic metre. The difference is scale. In an atomic nucleus, this density exists over femtometers. In a neutron star, it extends over kilometres. That's why neutron stars are so mind-boggling. They take the density of nuclear matter and make it the defining property of an entire astronomical object. Thinking about these limits raises interesting questions about the relationship between density and other cosmic boundaries. For example, as you approach the maximum density for matter, the escape velocity, the speed needed to break free from an object's gravity, creeps closer and closer to the speed of light. For black holes, it exceeds the speed of light entirely, creating the event horizon beyond which nothing can escape. This means that in a sense, neutron stars are just shy of being black holes, balanced precariously on the edge between matter and pure space-time curvature. The line between the densest possible matter and the onset of a black hole isn't just theoretical. Observations of unusually massive neutron stars, close to 2 solar masses or more, have forced astrophysicists to refine their models of what matter can withstand. The discovery of such heavy neutron stars means that the equations describing the behaviour of nuclear matter at high densities, called the equation of state, have to be stiff enough to prevent collapse up to those masses. At the same time, they must still allow for the eventual tipping point into black holes for heavier objects. These questions aren't just of academic interest. Understanding the limits of dense matter feeds into our knowledge of gravitational waves, stellar evolution, and even the distribution of elements in the universe. Every neutron star we study, every collision we observe, gives us more clues about where those boundaries really are. And while neutron stars mark the end of the road for matter as matter, they also point toward the next limit in our journey. The one defined not by what matter can endure, but by what happens when gravity wins completely. Because just beyond the densest allowed state lies the black hole wall, the ultimate no-return boundary in the cosmos, where density, gravity, and space-time itself merge into a single, inescapable phenomenon. Once you push matter beyond the threshold where even neutron degeneracy pressure can no longer hold back gravity, the universe doesn't give you many options. There's no intermediate, stable form. There's no almost neutron star but slightly denser state. Instead, gravity takes complete control, and the result is the most extreme object allowed by the laws of nature as we understand them, a black hole. The phrase black hole is so familiar now that it's easy to forget how strange it is. It's not really an object in the normal sense. When we talk about stars, planets, or neutron stars, we can describe their surfaces, their atmospheres, their internal structures. A black hole has none of that. It's defined entirely by a region of space, the event horizon, beyond which nothing can escape. Not light, not particles, not even information in any form. The interior, according to general relativity, contains a singularity, a point where density becomes infinite and space-time curvature is unbounded. Whether this singularity is a real feature of the universe, or a sign that our equations are incomplete, is one of the biggest unanswered questions in physics. The event horizon is sometimes described as the surface of the black hole, but that's misleading. It's not a physical surface you could land on. It's a boundary in space-time. If you cross it, you're inevitably carried toward the singularity. The escape velocity at the event horizon is exactly the speed of light, which is why nothing can get out once it's inside. From the outside, the horizon is perfectly black. No light from within can reach you, so you can never see what's going on beyond it. Black holes come in a range of sizes. Stellar mass black holes form when massive stars collapse at the end of their lives, typically with masses of a few times the Sun's and event horizons just a few kilometres across. Supermassive black holes found at the centres of galaxies can have masses millions or billions of times greater, with horizons larger than the entire solar system. There's also evidence for an in-between category, intermediate mass black holes, though these are harder to detect. In all cases, what defines the black hole isn't the size of the matter that fell in, but the curvature of space-time itself. Once the horizon forms, it's the geometry, not the matter, that traps everything inside. You could pour more material into the black hole, and the horizon would simply grow. Whatever details the matter once had, its chemical composition, its arrangement, are erased from the outside perspective. All that remains are three measurable properties: mass, electric charge, and spin. This no-hair theorem is one of the most remarkable features of black holes, and it's still an active area of research to understand exactly how information is hidden or transformed inside them. From the outside, black holes exert their influence in ways that are easier to grasp. Their gravity shapes the orbits of nearby stars, bends the paths of light, and can accelerate matter to extraordinary speeds as it falls inward. The accretion disks of material spiralling into black holes can be among the brightest objects in the universe, heated to extreme temperatures by friction and compressed magnetic fields. Jets of particles can shoot out from the poles of spinning black holes at nearly the speed of light, powered by the twisting of space-time itself. The wall we're talking about here, the event horizon, is as much a limit in physics as the speed of light or the Planck scale. Once something crosses it, it's gone from our universe in any practical sense. You can still describe what happens from the falling object's point of view, at least in theory. If you fell into a black hole, you wouldn't notice anything unusual as you crossed the horizon, provided it was a large black hole with a relatively gentle tidal gradient. But from the perspective of an outside observer, you'd appear to slow down and freeze at the horizon, your light becoming more and more redshifted until it faded away entirely. This discrepancy between perspectives is a hallmark of relativity, and one of the things that makes black holes so conceptually tricky. The horizon isn't a material barrier, but it's an absolute one. A boundary in the structure of space-time itself, in a very real sense. It's the edge of the observable universe for anything that crosses it, and it's one way only. The idea of a wall around black holes takes on another meaning when we consider the so-called firewall paradox. In 2012, some physicists proposed that quantum mechanics might require a searingly energetic boundary at the horizon, incinerating anything that tries to pass through. This would resolve certain puzzles about information loss, but would also violate the equivalence principle of general relativity, which says that falling through the horizon of a large black hole should feel unremarkable. The debate over firewalls is ongoing, and it underscores how black holes force us to confront the tension between quantum mechanics and relativity. There's also the question of Hawking radiation, the quantum process that allows black holes to slowly lose mass over time. Stephen Hawking showed in the 1970s that the event horizon isn't entirely black. Quantum fluctuations just outside it can result in pairs of particles, where one falls in and the other escapes, carrying away energy. Over vast timescales, this causes the black hole to evaporate. For stellar mass or larger black holes, this process is so slow as to be negligible. They take far longer than the current age of the universe to disappear. But for tiny, hypothetical black holes, Hawking radiation could be significant, even explosive. Hawking's discovery added a new twist to the idea of the black hole wall. It's not entirely impenetrable after all, at least not in the absolute sense. While nothing can escape classically, quantum mechanics allows for a slow leak. This raises the famous information paradox. If black holes evaporate completely, what happens to the information about the matter that fell in? Quantum mechanics insist that information can't be destroyed, but general relativity seems to say it can vanish into the singularity. Resolving this paradox has been one of the driving questions in theoretical physics for decades. What makes black holes so fascinating is that they sit at the intersection of so many cosmic limits. They represent the densest objects possible, beyond the reach of any pressure to resist collapse. They mark a boundary in space-time beyond which the concept of escape has no meaning. They challenge our understanding of how information is preserved in the universe, and they're not rare. The Milky Way alone likely contains millions of them, with a supermassive one, Sagittarius A, anchoring the galaxy's centre. From the perspective of cosmic limits, the black hole wall is a definitive endpoint for matter and light. It's the place where paths through space-time are cut off from the rest of the universe. But, like other limits we've explored, it's also a doorway to unknown physics. We don't know what happens inside the horizon. We don't know if singularities are real, or if they're replaced by something finite in a theory of quantum gravity. We don't know how to fully reconcile the demands of relativity and quantum mechanics at this boundary. And, intriguingly, the black hole wall isn't just a place where things end. It might also be a place where entirely new universes could begin. Some speculative ideas suggest that the interior of a black hole could pinch off into its own region of space-time, a kind of baby universe disconnected from ours. If that's true, then every black hole could be the seed of a cosmos, and our own universe might have originated in just such a process. These ideas remain speculative, but they capture the way black holes, for all their reputation as destructive voids, could also be cosmic creators. As strange and final as the black hole wall seems, it's not the only boundary of this kind in nature. There's another horizon, not wrapped around an object, but surrounding us everywhere we look. A horizon defined not by gravity's pull, but by the expansion of space itself. When we think about limits in the universe, brightness is one that feels easier to imagine. You've seen things that are dazzling, the midday sun, the flash of lightning close by, maybe the blinding glare of snow under a clear sky. But brightness, in the cosmic sense, can go far beyond anything our eyes have ever taken in. It's not just about how much light something produces, but about how much energy it can release in the shortest possible time. And in the same way, there's a ceiling for speed, a floor for cold, and a maximum density for matter. There's also a limit for how bright anything can get before physics steps in and says, that's enough. At its core, brightness is about energy per unit time per unit area. The sun's luminosity is about 3.8 10^126 watts, an extraordinary amount yet still far below the upper bounds nature can manage. Out in the universe there are explosions and outbursts so violent they make the sun look like a flickering candle. The champions of brightness are events like gamma ray bursts, supernovae, and certain types of magnetar flares, where vast amounts of energy are dumped into space in moments or minutes. But even these cosmic fireworks can't surpass what's called the Eddington limit, the maximum luminosity a star or any steady luminous object can sustain without blowing itself apart. This limit arises from a balance between the inward pull of gravity and the outward push of radiation. If a star produces light above this limit, the radiation pressure is so strong that it will drive away the material trying to fall inward. The exact value of the Eddington limit depends on the object's mass and composition, but for the Sun it's about 1.3 gong 1031 watts. Massive stars can shine brighter than the Sun by many orders of magnitude, but if they go too far above their own Eddington limit, they start shedding their outer layers in powerful winds. That's for steady sources of light. When it comes to brief, transient events, bursts rather than sustained glow, the ceiling is much higher. The brightest flashes ever recorded are gamma ray bursts, which can unleash as much energy in a few seconds as the sun will emit over its entire 10 billion year lifetime. These bursts come in two main types: long-duration bursts, thought to be caused by the collapse of massive stars into black holes, and short-duration bursts, likely from the merger of neutron stars or neutron stars with black holes. In both cases, the result is a narrow jet of high-energy radiation aimed directly at us, if we happen to be in its path. If you were close enough to one of these bursts, you wouldn't have time to notice. The flash of gamma rays would strip away atmospheres, boil oceans, and sterilize the surface of any planet in its reach. Fortunately, they're rare, and the universe is big. Still, we've detected them from billions of light years away, and even at that distance, they can temporarily outshine the rest of the observable universe in certain wavelengths. Another contender for the brightest possible event is a supernova, especially the hypernova variety. the death of a massive star producing an explosion far more energetic than a typical supernova. These can briefly rival the luminosity of an entire galaxy. The core collapse process that powers them releases an enormous amount of energy, though most of it escapes as neutrinos rather than visible light. For sheer electromagnetic output in a short time, gamma-ray bursts still win. On smaller scales, but no less impressive in their intensity, are magnetar flares. Magnetars are neutron stars with magnetic fields trillions of times stronger than Earth's. Occasionally, these magnetic fields twist and snap in a kind of starquake, releasing a pulse of gamma rays so intense that it can be detected across the galaxy. The most powerful magnetar flare ever recorded in 2004 came from a source 50,000 light-years away, yet briefly saturated detectors on multiple spacecraft. Had it been much closer, it could have caused serious effects in Earth's upper atmosphere. When we talk about the absolute brightest possible flash, we run into some of the same issues we've seen with other limits. Physics provides ceilings, but they depend on context. For a steady source, the Eddington limit applies. For an instantaneous release, the constraints come from the total energy available, how quickly it can be converted into radiation, and the fact that concentrating too much energy in too small a space risks forming a black hole instead of a flash. There's a tipping point where the energy density of the light itself becomes so high that its own gravity matters. Light has no rest mass, but it carries energy, and energy curves space-time. This means there's a practical upper bound even for momentary flashes. If you try to exceed it, the flash collapses into a black hole before it can fully escape. This is why discussions of the brightest possible event in theoretical astrophysics often circle back to the concept of the Planck luminosity, about 3.6 x 1052 watts. It's derived from fundamental constants and represents the absolute maximum power any event could, in principle, emit. Gamma-ray bursts come nowhere close to this number, which is a good thing. Something emitting at that level nearby would be instantly catastrophic. Brightness also depends on where you're standing. The Sun is overwhelmingly bright from Earth, but from Pluto it's just another bright star in the sky. Gamma-ray bursts are blinding if you're in the jet, but invisible if you're not. That's why brightest in astronomy often means most luminous in absolute terms, rather than what would hurt your eyes the most if you looked at it. The difference between luminosity, total energy output, and apparent brightness, how bright it looks to you, is important here. And it's the reason why a distant quasar, a supermassive black hole's accretion disk blazing at near its Eddington limit, can be brighter to our telescopes than a nearby star. From a cosmic limits perspective, the brightest possible flash is another place where extremes meet. You need huge amounts of energy concentrated in a small region and released over an incredibly short time scale, but you can't concentrate it so much that gravity traps it. You need a mechanism that can direct the energy efficiently. A focused jet is far more effective than a spherical blast, and you need conditions where the medium around the event doesn't immediately absorb or scatter the light. Gamma-ray bursts satisfy these conditions better than anything else we know, which is why they're the reigning champions in the universe we observe. There's also an intriguing connection between brightness limits and information limits. The faster you try to send information using light, the more power you need, but the more you push toward the brightness ceiling, the more likely you are to hit the gravitational constraint. In some ways, the absolute maximum brightness and the absolute maximum data rate are two faces of the same coin, both set by the fundamental constants of nature. Thinking about the brightest possible flash naturally leads to the question of what the universe itself looked like at its own brightest moment. That takes us back to the earliest instance after the Big Bang, when the entire cosmos was filled with radiation at energies far beyond anything we see today. In those first moments, there wasn't even any distinction between matter and radiation, just a seething plasma at or near the Planck temperature, expanding and cooling. In a sense, the Big Bang itself was the ultimate flash, though not one we could ever see directly. since light as we know it couldn't travel freely until hundreds of thousands of years later. From the dazzling heights of cosmic brightness, it's not a big leap to start thinking about the other end of visibility, the most perfect darkness possible, a place where no light at all can reach you. And in the universe, that's not just an empty void, it's a boundary defined by the expansion of space itself, a horizon that marks the limits of what we can ever hope to see. If the brightest flashes in the universe are over in seconds or less, there's an opposite kind of extreme that's no less fascinating. Lives that stretch not just for billions, but potentially for trillions of years. In the human frame of reference, even a few centuries is unimaginably long. Civilizations rise and fall in much shorter spans, and the oldest living things we know on Earth, certain bristlecone pines, a few ancient corals, have lifespans of thousands of years at most. But in the cosmos, where time is measured on scales so vast that stars and galaxies are the primary markers, there are objects that endure for spans we struggle to even conceptualize. Stars themselves offer a striking range of lifetimes. The most massive stars, burning through their fuel at a furious rate, can exhaust themselves in just a few million years, a cosmic blink. The Sun, a modest middleweight, has a projected lifespan of about 10 billion years, roughly halfway through its main sequence life. But it's the smallest, coolest stars, as the red dwarfs, that set the records. With masses just a fraction of the Sun's, they burn their hydrogen so slowly that their lives can stretch into the trillions of years. No red dwarf has ever died of old age because the universe itself is too young. They've all still got fuel to spare. These long-lived stars point to an important fact. In astrophysics, longevity is often about moderation. The less energy an object produces, the slower it uses up its available resources. A red dwarf's dim, steady burn means it sips its fuel instead of guzzling it. They also tend to be stable, without the kinds of violent outbursts that can shorten a star's life. The trade-off is that they're too faint to be visible to the naked eye from Earth unless they're extremely close. But in terms of sheer survival, they're unmatched among stars we can observe today. Beyond stars, the cosmos contains structures and objects that can persist for mind-boggling lengths of time. Take white dwarfs, for example, remnants of sun-like stars after they've shed their outer layers. These stellar embers no longer produce energy through fusion, but they still radiate heat. Over trillions of years, they cool and fade, eventually becoming so cold that they're effectively invisible. At that point, they'd be called black dwarfs, though none exist yet because the universe hasn't been around long enough for one to form. Then there are planets, moons, and other small bodies. Without internal sources of fusion, their lifespans are effectively determined by external factors like collisions or gravitational disruptions. A rocky planet orbiting a quiet red dwarf in a stable system could, in principle, survive for longer than any star in our galaxy has been alive. In the distant future, when all the stars have burned out, planets and brown dwarfs, failed stars that never ignited, will still be drifting through space, cooling toward the cosmic background temperature. On even larger scales, galaxy clusters and the dark matter halos that hold them together are likely to be among the longest-lived structures in the universe. The stars within them will come and go, but the gravitational framework of the cluster will persist for an almost unimaginable span, slowly changing shape as galaxies merge and their orbits decay. Even after the stars have gone dark, the cluster will still be there, a vast and mostly invisible arrangement of dark matter, black holes, and frozen remnants. The true champions of longevity, however, may be black holes. While they can evaporate over time via Hawking radiation, the timescales for this process are so immense that even a stellar mass black hole would take 1067 years to disappear. That's a 1 followed by 67 zeros. Supermassive black holes, like the one at the centre of our galaxy, would last even longer, up to 10 to 100 years or more. In the far future, when the last red dwarf has faded and the last white dwarf has gone cold, black holes may still be around, quietly holding on to the last gravitational structures in the universe. These numbers are almost too large to be meaningful. Our sense of time is rooted in personal and historical scales. Decades, centuries, perhaps a few millennia when we think about ancient civilizations. We can stretch to imagine the age of the Earth at 4.5 billion years and the age of the universe at 13.8 billion years. But trillions, quadrillions, and beyond take us into territory where human intuition stops being useful. At those scales, change is so slow that the universe feels static. The slow drift of stars, the gradual evaporation of black holes, the cooling of dead planets, all unfold over spans that dwarf the entire history of life on Earth. It's not just a matter of endurance for its own sake. The longest-lived objects in the universe also set the timetable for the universe's own story. As long as there are stars burning, galaxies have light and heat. When the last long-lived stars finally go dark, the universe will enter the so-called degenerate era, dominated by remnants. White dwarfs, neutron stars, black holes, and a scattering of cold, inert planets and asteroids. The pace of change will slow almost to a standstill, but it will never quite stop. One of the intriguing things about longevity is how it interacts with other cosmic limits. A star that's too bright burns out quickly. One that's dim enough can last almost forever by stellar standards. Black holes, which set records for density and gravitational pull, also set records for persistence. Even light, the fastest thing in the universe, can be trapped indefinitely in the right conditions, circling the event horizon of a black hole until it eventually leaks away through Hawking radiation. There's also a subtle point about lifespans in the cosmic sense. What we call the end for one object is often just the transformation into another. A massive star's death in a supernova might be over in seconds, but the neutron star or black hole it leaves behind will last for billions or trillions of years. A galaxy might lose its brightest stars quickly, but its dark matter halo will endure far longer. Even the proton, the building block of ordinary matter, might not be truly immortal. Some theories predict it could decay over timescales of 1034 years or more, a number so large that it's meaningless in everyday language. The longest possible lifespans, then, aren't just about records. They're about the shape of cosmic history, the way the universe paces itself over time. The short, brilliant lives of massive stars seed the cosmos with heavy elements, making planets and life possible. The long, quiet lives of red dwarfs and black holes ensure that the universe won't run out of structure for a very long time. Together, they form a kind of rhythm, bursts of creation and destruction on humanly unimaginable scales, followed by eons of quiet persistence. Eventually, of course, even the most long-lived things must end, at least in the universe as we understand it. The black holes will evaporate, the last particles may decay, and the cosmos will settle into a thin haze of low-energy photons, electrons and positrons, spread so far apart that they almost never interact. This far-future heat death isn't exactly a death in the biological sense. Nothing was ever alive in the way we are. But it marks the end of complexity, structure, and change. The longest-lived things will have stretched their existence across the entire arc of cosmic time, only to fade into the background. In any direction you look, the universe seems to go on, scattered with stars, galaxies, and faint smudges of light. The deeper our telescopes peer, the more ancient the light we collect, carrying messages from a time long before Earth even existed. But no matter how powerful our instruments become, there's a point beyond which we cannot see. It's not because our technology isn't good enough, or because there's nothing out there. It's because there's a limit set by the laws of physics themselves, the edge of the observable universe. The key word here is observable. The universe itself may be much larger than the part we can see, perhaps infinitely so. But because light travels at a finite speed, and the universe has a finite age, there's only a certain region from which light has had time to reach us since the beginning. Think of it like standing in the middle of a vast, dark plain with a flashlight that's only been on for a short time. The circle of ground it's illuminated represents the observable patch. Beyond that circle, the light simply hasn't had enough time to get there yet. In our case, the flashlight is the Big Bang, and the illuminated circle is nearly 46 billion light-years in radius. That number might seem strange at first, because the universe is 13.8 billion years old. Shouldn't the edge of the observable be 13.8 billion light-years away? The difference comes from the fact that space itself has been expanding all the while. Light from the most distant objects we can see was emitted billions of years ago, when those objects were much closer, but as the light travelled, space stretched, carrying those objects farther away. By the time the light reaches us, the source is now tens of billions of light-years distant. What we're actually seeing at the farthest limit isn't a galaxy or a star at all. It's the cosmic microwave background, the afterglow of the Big Bang. This faint radiation comes from a time about 380,000 years after the beginning, when the universe had cooled enough for electrons and protons to combine into neutral atoms. Before that moment, the universe was a hot, dense plasma, where light couldn't travel freely. It was constantly scattered by free electrons, making everything opaque. The edge we see is the surface of last scattering, the moment when light could finally stream through space unimpeded. If you imagine the observable universe as a sphere centered on us, that surface is what forms its outer shell. Every point in space has its own observable sphere, and they all overlap, but no one can see beyond their own horizon. It's not a physical barrier. If you were out there near the edge, you'd see a different patch of sky extending in all directions. It's a limit set by the relationship between light speed and the universe's age. In some ways, the edge of the observable universe is like the event horizon of a black hole. Not in the sense of trapping light forever, but in the sense of marking a boundary to what can be known from a given location. The analogy goes deeper if we consider that the universe's expansion isn't slowing down, but speeding up, driven by dark energy. This acceleration means there are galaxies whose light will never reach us, no matter how long we wait, because space between us and them is expanding faster than light can bridge the gap. The current observable limit is just the inner part of a larger cosmic event horizon, beyond which events can never influence us. This has an important consequence. The observable universe is getting larger in terms of distance. More ancient light is reaching us over time. But at the same time, the number of galaxies we can ever hope to observe is finite. As expansion continues, more and more galaxies will slip beyond the cosmic event horizon, disappearing from view forever. In the distant future, an observer in our galaxy might see only the local group of galaxies, with everything else gone, leaving them with no direct evidence of the wider cosmos. The edge of the observable is also a time boundary. The farther away we look, the further back in time we're seeing. At intermediate distances, we see galaxies in various stages of formation, giving us a kind of cosmic history book in reverse. At the farthest distances, we see the universe itself as a baby, still glowing with the heat of its birth. The fact that we can see this far is what allows cosmologists to test models of the early universe, measure the distribution of matter, and probe the nature of dark energy and dark matter. Yet beyond that visible edge, we know almost nothing. It could be more of the same, an endless continuation of galaxies, voids, and clusters, or it could be radically different, shaped by conditions we can't detect from here. If the universe is finite, it might curve back on itself, so that if you could somehow travel far enough, you'd return to your starting point. If it's infinite, then no matter how far you go, there's always more. But these are questions we may never answer directly, because the observable limit is, by definition, unbreakable without violating the cosmic speed limit. There's an odd comfort in this. The edge of the observable universe isn't about what's missing, it's about what's possible to know from our position in space and time. It's a reminder that even in a universe this vast, there are limits to knowledge. not because of human shortcomings, but because of the structure of reality itself. We live in a finite window into something that may be boundless, and everything we've ever known or seen is contained within it. In that sense, the edge is not a hard stop, but a frame. It gives shape to the universe as we experience it, defining the larger scales we can directly study. And it invites speculation about what lies beyond, not in a mystical sense, but in the curiosity that drives science forward. Even though we may never see past that horizon, our models can extend into the unobservable, testing possibilities against the patterns we see inside. When you think about limits in the universe, it's easy to picture them as physical boundaries. The fastest speed you can travel, the smallest unit of space, the furthest distance you can see. But there's another kind of a limit that's less tangible, yet every bit as real. The limit to how much information can exist in a given space. It's a boundary not of matter or energy, but of knowledge itself. At first, this might sound strange. Information isn't like a physical object that takes up room, is it? But in physics, information is inseparably tied to the arrangement and state of matter and energy. Every particle, every photon, every quantum field contains information about its properties and its history. If you want to store a bit of information, a simple yes or no, you need some kind of physical system to represent it. A mark on paper, a magnetic flip on a hard drive, the quantum spin of an electron, all require real, finite resources. That means there's a limit to how much you can pack into a given volume before you hit a wall. That wall is defined by the laws of thermodynamics and quantum mechanics, and most famously by something called the Bekenstein bound. Jacob Bekenstein in the 1970s was exploring the thermodynamics of black holes when he realised that there's an upper limit to the amount of information, or entropy, that can be contained within a finite region of space that has a finite amount of energy. He found that this limit is proportional not to the volume of the region, as you might expect, but to the surface area of its boundary, measured in tiny Planck-sized units. This was a shock. We usually think of storage capacity in terms of volume. A bigger hard drive means more bits, because you can fit more memory cells inside. But at the deepest level, the maximum information content of a region of space is determined by its surface area, not its bulk. This insight is one of the seeds of what later became the holographic principle, the idea that the information describing a volume of space can be thought of as encoded on its boundary, like a hologram. Black holes are the perfect example of this limit in action. If you throw matter into a black hole, you're increasing its mass and therefore its energy. According to Bekenstein's work, that means the black hole's entropy goes up, and this entropy is proportional to the area of its event horizon. The more massive the black hole, the bigger the horizon, and the more information it can, in principle, contain. Once the horizon reaches a certain size, you've hit the maximum capacity for that region. You can't cram in more information without expanding the horizon, which is to say, without making the black hole bigger. It's important to stress that this isn't about practical limitations, like how much data our computers can store today. It's about the absolute physical limits set by the nature of reality. You can't bypass it with better technology because it's not a matter of engineering. It's baked into the laws of physics. Just as you can't accelerate a particle past the speed of light no matter how much energy you pour in, you can't exceed the information density limit without changing the very structure of the space you're using. There's another connection here to energy. Landauer's principle, from information theory, says that erasing a single bit of information requires a minimum amount of energy, proportional to the temperature of the system. This ties the abstract concept of information to thermodynamics in a concrete way. If you try to store and process more and more data in a finite system, the heat generated becomes a serious constraint. At the ultimate densities described by the Bekenstein bound, this isn't just a problem. It's a fundamental limit. In the cosmic context, this means that the universe itself has a finite information capacity. There's only so much detail that can exist inside the observable universe. even if it's unimaginably vast. If you try to imagine storing every possible detail of every particle's position and state, you'd quickly find that you run into this limit. It's not infinite resolution all the way down. There's a finite number of bits the universe can hold, set by its size and energy content. This has profound implications for our understanding of reality. If the total information content is finite, then in some sense the universe is like a giant computer with a fixed memory size. Every event, every object, every arrangement of matter and energy is part of the data stored in that cosmic memory. The laws of physics are like the operating system, updating the state of the system from moment to moment. And just like with a real computer, there are constraints on how much can be stored, processed, or retrieved at once. It also means that perfect measurement is impossible. You can't specify the position and velocity of every particle to infinite precision, because that would require infinite information. Quantum mechanics already tells us that certain properties can't be known exactly at the same time, the uncertainty principle. But the Beaconstein bound adds another layer, telling us that even if you tried to keep track of everything you could measure, there's only so much capacity available in the universe. Some physicists have speculated that this finite capacity might explain certain puzzles, like why space-time itself might be discrete at the smaller scales. If there's a maximum amount of information you can have in a given volume, then below a certain scale, there simply isn't room for more detail. This could mean that space and time aren't smooth continua, but rather built from finite chunks, the Planck scale, pixels of the universe. The connection between information and physical limits becomes even more intriguing when we think about computation. The Margolis-Levitin theorem, for example, says that there's a maximum rate at which any physical system can perform distinct operations based on its energy. This sets an upper bound on the speed of any possible computer, whether made of silicon, quantum bits, or something more exotic. Combine this with the Beaconstein bound, and you get a ceiling on both how much can be stored and how fast it can be processed in any region of space. In a way, the limit of information is the most universal of all the cosmic limits, because it applies to every other one. The maximum brightness of a flash is connected to how much information about the system can be carried away in light. The shortest tick of time is tied to how quickly information can change state. The densest matter possible carries the maximum information density in a given space before collapsing into a black hole. Even the edge of the observable universe is ultimately an information boundary. Beyond it, there are events we can never know about, because no signal can ever reach us. Thinking about the universe as an information-limited system doesn't diminish its mystery. If anything, it deepens it. It suggests that the structure we see, from galaxies to subatomic particles, is part of a vast and finite arrangement of information, evolving according to precise rules. It hints that the limits we encounter in physics are not arbitrary, but reflections of the same underlying principles, just expressed in different forms. If information has an ultimate limit, then energy, the ability to do work, to move matter, to change the state of thing, must also have one. In everyday life, we don't run into this ceiling. We talk about maximum power ratings on engines or energy efficiency in appliances, but those limits are practical, not fundamental. You can always build a stronger motor or a bigger generator, as long as you have the materials and fuel. But on the deepest level, nature imposes an absolute cap on how much energy can be packed into a given space, and by extension, how much total energy is possible in a single event. To get there, you have to start with the fact that energy and mass are interchangeable, as Einstein's famous E-mc2 tells us. That equation is often quoted, but its implications go beyond the idea that mass can be turned into energy. It also means that any concentration of energy has mass, and therefore it has gravity. The more energy you pile into a small volume, the stronger the gravitational pull of that region becomes. Push this far enough, and you hit a critical point. The energy density becomes so large that it forms a black hole. This gives us a natural hard ceiling for energy density. If you try to exceed it in a given space, the space collapses into its own event horizon. The limit is set by the Planck energy scale, about 1.26 skeg 1019 giga-electron volts, unimaginably higher than anything we can reach with our particle accelerators today. In human-built machines, the most energetic collisions we've ever made are at the Large Hadron Collider, which reaches a few trillion electron volts, still 16 orders of magnitude below the Planck energy. That's not just a matter of funding or technology. It's the difference between stirring the surface of a pond and trying to churn the ocean. The Planck energy is connected to the Planck length and Planck time, the smallest meaningful units of space and time according to our current understanding. At those scales, quantum mechanics and general relativity are both equally important, and our present theories are incomplete. It's often said that the Planck scale is where we'd need a theory of quantum gravity to describe what happens, because the gravitational effects of individual quanta become impossible to ignore. If we could somehow collide particles at the Planck energy, the result would be so dense with energy that it would either form a tiny black hole or reveal an entirely new regime of physics. It's tempting to imagine that we could just build a bigger and more powerful accelerator to explore these energies directly, but the numbers make that impractical in ways that verge on the absurd. To accelerate a single particle to the Planck energy with current technology would require a ring of magnets bigger than the observable universe. Even if you invented a more efficient method, the sheer energy storage required would dwarf anything a planet, let alone a civilization, could muster. In nature, the universe has its own ways of getting close to these extremes. The most energetic cosmic rays ever detected, the so-called oh my god particle, and others like it, carry energies in the range of 1020 electron volts. That's far beyond what we can make on Earth, though still well below the Planck energy. We don't yet know exactly what accelerates these particles to such speeds, but the likely candidates are violent astrophysical environments like active galactic nuclei, the shock waves of supernovae, or the magnetic maelstroms around rapidly spinning neutron stars. Even these natural accelerators have ceilings, and they're set by the same interplay of energy, mass, and gravity. To accelerate a particle, you need a region of space with intense magnetic or electric fields, and those fields require energy to exist. Push them too far, and you start distorting the space-time they sit in. If you could somehow cram more and more energy into that particle beam, you'd eventually cross the threshold where the accelerator itself would collapse into a black hole. That's the point where physics says no more. There's another angle to energy limits that comes from thermodynamics rather than gravity. Temperature is, at its core, a measure of the average kinetic energy of particles. The higher the temperature, the more energetic the particles are. At ordinary scales, there's no upper bound. You can always imagine adding more energy and making it hotter. But in quantum field theory, there's a practical limit called the Planck temperature, about 1.42 x 1032 kelvins. Above this, the wavelengths of the particles are so short and their energies so high that quantum gravitational effects dominate, and our current physics breaks down. This temperature isn't just hot. It's the point where hot, as we understand it, stops being a meaningful description. The early universe reached something close to this immediately after the Big Bang. In the first fractions of a second, the energy density was so high that all forces except gravity may have been unified into a single interaction, and space-time itself was fluctuating on quantum scales. Whatever physics operated in that regime has left imprints in the structure of the cosmos today, but we only see them indirectly. Directly recreating those conditions is beyond any hope of an experiment with matter as we know it. The ceiling on energy density is also a ceiling on power. How much energy can be delivered in a given amount of time? This is where the Planck power comes in, about 3.63 × 1052 watts. This is the maximum possible power output according to our current laws of physics. A gamma-ray burst, one of the most luminous events we know of, might reach a fraction of this, but no known event in the observable universe sustains it. If something did reach this limit, it would either be over almost instantly, or be indistinguishable from a black hole forming. Interestingly, the limits on energy, temperature and power all tie back to the same fundamental constants: the speed of light, Planck's constant, and the gravitational constant. These constants link the seemingly separate domains of relativity, quantum mechanics, and thermodynamics into a single framework. The fact that the same numbers set the ceilings for so many different extremes is a clue that these are not arbitrary constraints but deeply embedded features of reality. In thinking about energy's hard ceiling, it's worth noting that most of the universe operates nowhere near it. The Sun, with its enormous output, converts only a tiny fraction of its mass into energy each second, and the resulting density in its core is far from the black hole threshold. Even the most violent supernova is orders of magnitude below the Planck density. In a way, that's what allows complexity to exist. If every energetic event instantly pushed to the maximum, the universe would be nothing but a haze of black holes. But the ceiling is still there, looming in the background of physics. It sets the outer boundary for what can be built, what can happen, and what can exist. It's the line between the extreme and the impossible, the point where nature's rules shift into a mode we don't yet understand. Whether it's a tiny black hole popping into existence in a particle collision, or the entire cosmos compressed into the first instant of the Big Bang, the hard ceiling on energy is where our current theories hit their breaking point. When we talk about speed limits in the universe, the first and most famous one is the speed of a light in a vacuum, about 219 to the 792 kilometers per second. It's the fastest any particle or signal can travel through space according to relativity, and it's woven into every part of modern physics. But there's another kind of limit that often confuses people: the fact that space itself can expand in a way that seems to outrun light, and yet not violate the cosmic speed limit. To understand this, we have to separate the idea of motion through space from the stretching of space itself. In everyday life, speed is always measured against something. A car moves at 100 kilometers per hour relative to the road. An airplane moves at 900 kilometers per hour relative to the air. Light moves at its maximum speed relative to any observer, regardless of their motion. This is the bedrock of Einstein's special relativity. But when we deal with the universe on the larger scales, we're not talking about things moving through a fixed stage called space. Space itself is dynamic, and it can expand or contract. The expansion of the universe is described by general relativity, which doesn't put a limit on how fast distant points in space can recede from each other due to this stretching. If you imagine a balloon being inflated with dots drawn on it, the dots move apart not because they're crawling over the surface, but because the surface itself is stretching. In that analogy, there's no speed limit on how fast a surface can be stretched, and the same is true for space. This is why galaxies beyond a certain distance are receding from us faster than the speed of light. Not because they're breaking the rules, but because the rules apply to motion through space, not to the expansion of space itself. Light they emit now will never reach us, because the space between us and them is expanding too quickly. This is the origin of the cosmic event horizon we touched on earlier, the ultimate boundary of what can influence us. The rate at which space expands is given by the Hubble constant, which tells us how fast galaxies are receding for each megaparsec of distance. But this isn't a fixed number forever. It changes over time. In the early universe, during a phase called inflation, space expanded so quickly that regions once in contact were pushed far beyond each other's horizons in a fraction of a second. The speed of that expansion dwarfed anything we see today, yet it didn't violate relativity because nothing was travelling faster than light through space. The space itself was simply growing. The current expansion is much slower than inflation, but it's not slowing down the way we once thought. Observations of distant supernovae in the late 1990s revealed that the expansion is actually accelerating, driven by something we call dark energy. This means that over time, more and more of the universe will slip beyond our reach, no matter how fast we try to travel toward it. The acceleration will push galaxies away faster than light can bring their signals to us, making the observable universe effectively shrink in terms of the number of things it contains. This idea, that there's a speed limit for motion but not for expansion, sometimes makes people think we could use expansion as a kind of loophole to travel faster than light. Science fiction often plays with this in concepts like warp drives or wormholes. In theory, if you could create a region of space that expanded behind you and contracted in front of you, you could effectively move faster than light relative to distant objects without breaking local speed limits. But making such a thing work in practice would require manipulating space-time on scales far beyond anything we can do, and according to our current understanding, it would require exotic forms of matter with negative energy density, something we haven't observed in the necessary quantities. On a practical level, the cosmic expansion speed limit means that there are parts of the universe we can never reach, even with an infinitely advanced spacecraft. There's a sphere around us, about 16 billion light-years in radius in comoving distance, beyond which galaxies are already receding faster than light. Anything beyond that sphere is effectively cut off forever, not because it's infinitely far away now, but because the expansion will always outpace any attempt to catch up. It's a strange thought. The universe is vast, possibly infinite, but our future light cone, the region we can ever interact with, is finite. In a few tens of billions of years, only the galaxies bound to our own will remain visible, and the rest will have slipped over the horizon. The night sky will look empty and dark, not because the stars have gone out, but because their light can no longer bridge the expanding gap. This also ties into the way we measure distances in cosmology. There's the proper distance, which is how far something is right now, if you could freeze the expansion, and there's the light travel distance, which is how far the light has come since it was emitted. Because the expansion changes over time, these numbers don't match in the way they would in a static universe. A galaxy whose light took 13 billion years to reach us might now be 30 billion light-years away, and still moving away faster than light. The cosmic expansion speed limit isn't really a limit in the same way as the speed of light. It's more like a structural feature of the universe, a consequence of how space and time are linked in general relativity. The limit that matters locally, no object with mass can move faster than light relative to its immediate surroundings, still holds everywhere. But globally, the geometry of space-time can change in ways that make distant regions recede at any rate. It's worth noting that if the acceleration of the universe continues unchecked, we might one day face an even more extreme limit, the so-called Big Rip scenario. In this speculative model, dark energy's influence grows so strong that it doesn't just push galaxies away from each other, it eventually overcomes all other forces. Galaxies, solar systems, planets, even atoms would be pulled apart as space expands faster and faster everywhere. Most cosmologists think this isn't the fate we're headed for, but it's an example of how the rules of cosmic expansion can push the concept of a speed limit to its breaking point. So while nothing can outrun light through space, the expansion of space itself plays by a different set of rules, allowing the universe to carry objects apart at superluminal speeds without contradiction. This is one of those ideas that's counterintuitive at first, but once you grasp it, it becomes a key to understanding why the universe looks and behaves the way it does. When you think of limits in the universe, computation might not be the first that comes to mind. But if you step back and think of the universe itself as a vast information processor, constantly updating its state according to the laws of physics, then it becomes clear that there's a maximum rate at which those updates can happen. This is the ultimate computational limit, a boundary not of machines we build, but of the very fabric of reality. We can start with the way computers work in the everyday sense. Whether it's a laptop or a supercomputer, a device processes information by moving bits through logical operations. The faster it can do that, the more problems it can solve in a given amount of time. For decades, the speed of computation has climbed steadily, driven by smaller transistors, better materials, and more parallel processing. But this progress has always been bounded by physical limits. The speed of electrical signals, the amount of heat you can dissipate, the reliability of components. If you strip away the engineering specifics and look only at the physics, there's an absolute bound that applies to any computational device in the universe. It comes from the combination of quantum mechanics and relativity, and it's known as the Margulis-Levitin limit. This theorem says that the maximum number of distinct operations a system can perform per second is directly proportional to its energy, and the constant of proportionality comes from Planck's constant, the same number that governs quantum behaviour at the smallest scales. In practical terms, this means that if you have a system with a certain amount of mass energy, there's a hard cap on how quickly it can change from one distinguishable state to another. For a 1 kilogram mass of perfectly efficient computing matter, the maximum rate is about 5.4 for 1050 operations per second. That's an absurdly large number compared to anything humans have built, but it's finite. No matter how clever you are, you can't exceed it without adding more mass or energy. The other key piece of this puzzle comes from the Bekenstein bound, which we've already touched on when talking about the limit of information. That bound tells you the maximum number of bits that can be stored in a given region of space with a given amount of energy. Combine the Bekenstein bound, storage, with the Margulis-Levitin limit, processing speed, and you get the ultimate ceiling on how powerful a computer can be. This isn't a matter of technology or design. It's baked into the laws of physics. If you wanted to build the fastest possible computer using all the resources of Earth, you'd have to convert the planet into something close to a black hole to reach the upper bound. A black hole, in fact, is often considered the ultimate computer in a purely theoretical sense. Its entropy, proportional to its horizon area, measures the maximum amount of information it can contain, and Hawking radiation could, in principle, serve as a way to process and output that information. A black hole of Earth's mass could perform about 1075 operations per second, orders of magnitude beyond any conceivable artificial machine. But there's a catch. Such a computer wouldn't be practical. You can't program a black hole in the usual sense, and retrieving information from it would be an exercise in patience, measured in evaporation timescales far longer than the age of the universe. The ultimate computational limit is more a theoretical boundary than a blueprint. It tells us what's possible in principle, not what's useful in practice. Even so, this concept has surprising implications when you think about the universe as a whole. If the observable universe contains about 1080 particles and has existed for 1017 seconds, then the total number of possible operations since the Big Bang, assuming it's been running at the maximum possible rate, is on the order of 120. That's a huge number, but it's not infinite. It means that in 13.8 billion years, the universe has had only a finite number of computational steps to evolve from its initial state to the present. This finite computational capacity places constraints on the complexity of things that can exist. You can't have a process that requires more operations than the universe has had time to perform. It also hints at why certain things, like perfect simulation of the universe in all its detail, are impossible. You'd need a computer bigger than the universe itself to keep up. Even a hypothetical civilization far more advanced than ours would be bound by these same rules. They could build faster and denser computers, but never ones that surpass the ultimate limits without increasing the mass energy they control. One interesting thought experiment that comes out of this is the idea of computronium, matter optimized at the atomic or subatomic level for maximum computation. In theory, you could take all the atoms of a planet or a star and arrange them into the most efficient computing structure possible, reaching close to the Bekenstein and Margulis-Levitin bounds for that mass. In practice, we're nowhere near that level of control over matter, and there are all sorts of engineering challenges that would get in the way. But the physics says there is a definite ceiling, and computronium would be the way to approach it. At the cosmic scale, some have speculated that the universe itself might be doing something like this. that reality is, in a sense, the output of a vast computation obeying these fundamental limits. Whether you take that literally or metaphorically, the fact remains that every change in the universe's state is subject to the same bound-on rate and storage. This universality is what makes the ultimate computational limit so profound. It applies equally to human-made processors, to hypothetical alien supercomputers, to black holes, and to the evolution of the cosmos itself. There's a kind of symmetry in seeing these limits together. The speed of light limits how fast information can travel between processors. The Bekenstein bound limits how much information can be stored. The Margolis-Levitin limit caps how fast that information can be processed. And energy's hard ceiling sets the upper bound on how much mass energy you can devote to the whole enterprise. Each one is a piece of the same puzzle, and together they define the maximum pace at which the universe's story can unfold. If the universe imposes limits on speed, energy, information and computation, it shouldn't be surprising that it also sets limits on life. Life, after all, isn't exempt from the laws of physics. It's built from the same atoms as everything else, organised into complex arrangements that maintain themselves far from equilibrium by taking in energy and shedding waste. And like any physical process, there are extremes it can't survive. Temperatures, pressures, and radiation levels beyond which the delicate chemistry of living systems breaks down. But here's the remarkable thing. Those limits are far wider than we once thought. On Earth, we've discovered organisms thriving in places where no one expected them. Boiling hot springs, deep-sea vents under crushing pressures, rocks miles below the surface, and ice fields in perpetual darkness. These so-called extremophiles have pushed our understanding of life's range, forcing us to reconsider where life might exist elsewhere in the universe. Temperature is one of the clearest boundaries. Proteins, the molecular machines of cells, rely on specific shapes to function. Heat can cause those shapes to unravel, a process called denaturation, while cold can slow down chemical reactions to a near halt. For most familiar life, liquid water is a necessity, so the usual range for active metabolism is between degree and 100 a year under Earth-like pressure. But certain thermophiles, like those found in hydrothermal vents, can function at temperatures above 120 degrees Celsius, thanks to specially adapted enzymes and heat-stable membranes. At the other extreme, psychrophiles in Antarctic ice can metabolize slowly even at 120 degrees, with anti-freeze-like proteins keeping their internal fluids from freezing solid. Pressure sets another set of boundaries. At the bottom of the Mariana Trench, pressures exceed 1,000 times that at sea level, enough to crush most submarines. Yet piezophils, pressure-loving microbes, not only endure these conditions but require them for proper function. Their proteins and membranes are adapted to stay flexible and active under immense compression. On the other side, some organisms can survive in the near vacuum of space for limited periods, as shown by experiments exposing microbes and tiny animals called tardigrades to the harsh environment outside the International Space Station. Radiation is another killer for most life. High-energy photons and particles can break chemical bonds, shred DNA, and damage cellular machinery. But even here, some organisms have remarkable defences. Deinococcus radiodurans, for example, can survive radiation doses thousands of times higher than those lethal to humans, thanks to efficient DNA repair systems and protective antioxidants. These adaptations hint at the resilience life can evolve when its survival depends on it. Desiccation, the complete removal of water, is yet another boundary. Water is the medium for almost all biological chemistry, so drying out typically halts life's processes. Yet some organisms can survive complete dehydration by entering a dormant state. Tardigrades again are famous for this, curling into a ton called a cryptobiosis state, in which their metabolism drops to near zero. They can remain like this for years, even decades, and revive when water returns. While these adaptations stretch the limits of life on Earth, they don't abolish them. Proteins still lose their structure at high enough heat. Membranes still become rigid and fragile at extreme cold. Radiation eventually damages beyond repair if it's intense enough. And even the hardiest microbe needs some minimum amount of energy and molecular stability to function. There's no living system that can survive the core of a star, the vacuum near a black hole's event horizon, or the searing Planck temperature moments after the Big Bang. These boundaries have implications for the search for life beyond Earth. Planets and moons with conditions near the extremes we've seen on Earth are now seen as more plausible candidates for habitability. Europa, with its icy crust and subsurface ocean, might host life adapted to cold and darkness. Enceladus, with its geysers and possible hydrothermal activity, could offer conditions like deep-sea vents. Even the scorching clouds of Venus have been considered for hypothetical microbial life, given that some Earth microbes tolerate acidic and hot environments. The boundaries also help us think about what life really means. Our definition is based on carbon chemistry and water, but it's possible that other biochemistries could shift these limits. Silicon-based life, for example, is often imagined in science fiction because silicon can form long chains like carbon, though in reality its chemistry is less flexible. Ammonia, methane or other solvents could support metabolism at much colder temperatures than water, expanding the range of possible habitats. But no matter the chemistry, the same fundamental physics applies. Molecules need stability, reactions need energy, and too much or too little of that energy will disrupt the system. It's tempting to wonder if life could adapt to cosmic extremes beyond anything we know, perhaps using mechanisms we haven't yet imagined. Could something survive inside the accretion disk of a black hole, feeding on magnetic turbulence and radiation? Could life emerge in the thin plasma between galaxy clusters, where temperatures are high but densities are so low that collisions between particles are rare? The known boundaries suggest that while such scenarios are fascinating, they'd require overcoming challenges at the very edge of what's physically possible for complex chemistry. The ultimate boundaries of biological life are therefore shaped by the interplay between environmental conditions and the molecular structures that make life possible. They're not arbitrary, they're set by the laws of thermodynamics, chemistry, and physics. And even the most extreme adaptations we know about are still bounded by these principles. What's striking is how life seems to find every available niche within those boundaries. Wherever there's a stable supply of energy and a medium for chemistry, life on Earth has managed to take hold, even if that environment would be instantly lethal to most organisms. This resilience suggests that if life can emerge in one place, it's likely to spread into every corner it can reach, until it runs into the true limits. Some limits in the universe are concrete and measurable. We can point to a thermometer and say this is the hottest something has ever been in a laboratory, or shine a particle beam and know exactly how much energy it carries. But there's another category of limits that exist not because we've measured them, but because the mathematics of our theories suggest they must be there. They're like signposts at the end of a road that read no passage, not because we've driven there and seen the drop-off, but because the map itself shows the cliff. These are the theoretical walls, barriers that seem to be built into the way reality operates, which may be forever beyond our reach. One of the most famous is cosmic censorship. This principle, proposed in the late 1960s by Roger Penrose, says that singularities, the infinitely dense points predicted to exist at the centres of black holes, must always be hidden from the outside world by an event horizon. Without this rule, a so-called naked singularity could exist, exposing a place where the laws of physics break down to direct observation. That would be troubling for general relativity, because a singularity's gravitational pull could be so extreme and unpredictable that it would make the future evolution of the universe in that region unknowable. The cosmic censorship hypothesis isn't proven, but so far every realistic scenario we've modelled seems to obey it. It's as if nature keeps its most chaotic regions politely behind a curtain. Another wall is the unitarity principle in quantum mechanics. This is the idea that the total amount of probability in a quantum system always adds up to 1, and that information about a system's past is never truly lost. It's preserved in the evolution of the wave function. This becomes especially contentious when you mix quantum mechanics with black holes. Stephen Hawking famously showed that black holes emit radiation and can evaporate over time, which seems to lead to a paradox. If the radiation is purely thermal, it carries no information about what fell in, meaning that when the black hole disappears, that information is lost forever. This would violate unitarity, something quantum mechanics doesn't allow. The black hole information paradox has been debated for decades, and while many physicists suspect that the information must somehow be preserved, perhaps encoded in subtle correlations in the radiation, the exact mechanism remains a mystery. Until we know, the preservation of information stands as a theoretical wall we believe exists, but can't yet fully see. Then there's the limit set by the uncertainty principle. Heisenberg's formulation tells us that we can't simultaneously know certain pairs of properties, like position and momentum, with arbitrary precision. This isn't a matter of better measurement tools, it's a feature of reality itself. Trying to pin down one of those properties more precisely inevitably blurs the other. At small scales, this is more than a nuisance. It's the reason atoms are stable, why electrons don't spiral into nuclei, and why quantum systems have a kind of built-in fuzziness. It's a wall we're constantly aware of because it defines the very structure of matter. The second law of thermodynamics is another. It says that the total entropy, the measure of disorder, or the number of possible arrangements of a system, never decreases in an isolated system. You can locally decrease entropy by doing work, but the overall entropy of the combined system plus environment always rises. This isn't a law in the sense of being enforced by a cosmic policeman. It's a statistical truth that emerges from the sheer number of possible states. In theory, you could get a local fluctuation where entropy decreases, but the odds are so low for anything significant that for all practical purposes the second law is an unbreakable wall. It's what gives time its arrow, ensuring that the past and future have a direction. We also have what are called no-go theorems, results in physics and mathematics that prove certain things can't happen under specific assumptions. For example, the Coleman-Mandula theorem says that the symmetries of space-time and the symmetries of internal particle properties can't be combined in certain ways unless the theory is trivial. This might sound abstract, but it places deep constraints on what a unified theory of physics could look like. Similarly, the Bell inequalities and their experimental violations tell us that any hidden variable theory of quantum mechanics must be non-local, meaning that it can't respect both the principle of locality and the predictions of quantum mechanics at the same time. These theorems are like walls drawn on the blueprint of possible theories, carving out the shapes they can take. Then there are limits born from the combination of general relativity and quantum field theory, the two great frameworks of modern physics that don't yet play nicely together. For example, we strongly suspect there's a limit to how small a region of space can be before quantum gravitational effects dominate. That's the Planck length, and it's where our current theories simply stop giving reliable answers. It's not that something physically blocks us from looking smaller. It's that the mathematics collapses into nonsense when we try. It's a wall of ignorance, one we might move by inventing a better theory, but for now, it's absolute. In some cases, these walls might not be fundamental after all. They might be temporary scaffolding, boundaries drawn in our current models that a future theory will redraw. For example, the speed of light in a vacuum is absolute for any object with mass. But in the early days of physics, people thought there might be ways to slip around it. Special relativity closed that door, but general relativity opened another one. While you can't travel faster than light through space, space itself can expand faster than light. That wasn't breaking the wall, it was finding out that the wall had a shape we didn't expect. The most tantalizing question about these theoretical limits is whether they're truly inviolable, or just markers for the edge of our understanding. Cosmic censorship might fall if we find a realistic process that produces a naked singularity, and if that happens, we'd need new physics to describe it. The black hole information paradox might dissolve when we finally have a full theory of quantum gravity, perhaps showing that information is never lost in a deeper sense. Even the uncertainty principle, which seems as fundamental as any, might one day be understood as a consequence of something more basic, though it's hard to imagine physics without it. The danger in treating these boundaries as immutable is that it can discourage exploration, but the danger in assuming they can be crossed is that it can lead to chasing impossibilities. The art of physics is often in deciding which limits are there to be tested and which are part of the bedrock of reality. Sometimes that decision is made by theory, sometimes by experiment, and sometimes, frustratingly, by the fact that the conditions needed to test a limit are so extreme we can't reach them. Still, history shows that what we think of as an ultimate wall today may turn out to be a doorway tomorrow. The speed of sound was once thought of as a natural limit, until technology developed to surpass it. The same could be true for certain impossible regions of physics. But there will almost certainly remain boundaries we can approach forever without crossing, like the speed of light for objects with mass, or the impossibility of reversing entropy on a macroscopic scale. These are the lines reality has drawn, the ones that keep the structure of the cosmos coherent. And so, as we stand before these theoretical walls, we're reminded that the universe isn't an open field without boundaries. It's a landscape with ridges, cliffs, and sheer drops, some visible, some hidden in fog. Our path winds between them, sometimes right up to the edge, sometimes turning back, and even if we never breach them, the act of walking toward them, of probing their contours, is part of what gives science its shape. It's only natural to consider the role of limits not as obstacles, but as defining features, the way they give the universe structure, stability, and perhaps even beauty. In the end, the absolute cosmic limit might not be a single wall, but the entire pattern of boundaries that make the universe what it is. For much of human history, limits have been seen as obstacles to overcome. They were the borders on maps, the boundaries of kingdoms, the edges of our technology. When we reached them, we tried to push them back. The horizon at sea was once the edge of the known world, and the idea of travelling beyond it carried both wonder and fear. In science, limits have played a similar role. They're the numbers and principles we discover, and then spend generations testing, trying to see if they can be moved. But as we've explored the deepest laws of physics, we've found limits that aren't just technological hurdles. They're not waiting for better tools or more clever designs. They're part of the scaffolding of reality itself. The speed of light, the Planck scale, the Bekenstein bound, the second law of thermodynamics. These are not lines painted on the floor, they're the floor. And once you understand that, your relationship with limits changes. There's a strange kind of comfort in knowing that some things are fixed. In a universe where so much is in motion, where galaxies drift, stars burn out, and worlds change beyond recognition, these limits are constant. The speed of light has been the same for billions of years. The Planck length hasn't shrunk or stretched. Entropy has never reversed its arrow. These constants are part of what makes the universe predictable enough for life and thought to exist in the first place. Imagine if there were no such boundaries. If there were no speed limit, then the rules of cause and effect would crumble. Signals could arrive before they were sent, and the sequence of events could become meaningless. Without the second law of thermodynamics, time would lose its direction, and the processes that sustain life would have no natural flow. If the uncertainty principle didn't exist, atoms could collapse, chemistry as we know it wouldn't form, and the universe would be a radically different place, possibly one without complexity at all. The limits aren't just constraints, they're guardians of structure. They carve out a space where things can happen in a coherent way. They prevent extremes from overwhelming the balance that allows stars to shine steadily, planets to orbit for billions of years, and life to evolve. Without them, the cosmos might be nothing but chaos, either collapsing into stillness or blowing apart into noise. And there's something deeply human about learning to live within limits. Every life has boundaries, in time, in ability, in perspective. We may not be able to travel faster than light or know the exact position and momentum of every particle, but we can work within those bounds to understand more and more of what's possible. In some ways, the boundaries of the universe mirror the boundaries of the self. They're reminders that we don't have to see or do everything to find meaning. When we discover a new limit, our first instinct is often to see it as a challenge. And sometimes it is. Sometimes limits are thresholds we eventually cross when we learn more. But many of the absolute limits we've discussed aren't going anywhere. They're woven into the fabric of space, time, and energy. They define the landscape we live in. And once you accept that, you start to see that exploration isn't only about breaking boundaries. It's also about learning the terrain so well that you can move through it with clarity and purpose. In this way, limits are not the end of curiosity. They're its framework. Knowing the speed of light doesn't make space less interesting. It makes the ways light interacts with space richer. Knowing that entropy always increases doesn't make the study of thermodynamics dull. It makes the rare, local decreases in entropy, like the order created in living systems, even more fascinating. When you understand the boundaries, you can start asking deeper questions about what can happen inside them. There's also a quiet reassurance in realizing that the universe is not infinite in every way. The observable universe contains only a finite amount of information. There's a maximum energy density, a maximum brightness, a maximum speed. Even the expansion of space has its own structure and limits. It means that, in principle, there's a comprehensible shape to reality. We may never map it completely, but it isn't boundless chaos. It's a system with edges and laws. Sometimes, late at night, when we imagine the vastness of the cosmos, it's easy to feel small and unmoored. But the limits give us a kind of anchor. They tell us that no matter how far you go, there are rules that hold steady. Whether you're looking at a distant galaxy or the movement of atoms in your own body, the same constants apply. That unity, that consistency, is part of what makes science possible, and in a way it's part of what makes beauty possible too. A song is shaped by the limits of its scale and rhythm. A painting is defined by the edges of its canvas. A story unfolds within the bounds of its language. The universe's limits are like that. They give form to what would otherwise be formless. Without them, we might not have galaxies, stars, planets, or the intricate chain of events that led to life. It's tempting to think that if we could somehow remove all limits, we'd open the door to an endless set of possibilities. But the truth is, without boundaries, possibility itself loses shape. Limits don't just close doors, they define the corridors we can walk down, the rooms we can explore. And as history has shown, even within those corridors, the variety and richness of what's possible is staggering. So when we speak of the absolute cosmic limit, maybe it's not a single number or a single boundary. Maybe it's the collection of all these edges, the speed limit of light, the smallest possible tick of time, the most intense burst of energy, the farthest we can see. Together they create the outline of the universe we inhabit. And rather than being something to resent, that outline can be a source of wonder. Because the limits are not just barriers to our reach, they're the reason there's something to reach for in the first place. They make the universe stable enough for mountains to rise, rivers to flow, minds to form, and questions to be asked. They give us the stage on which every act of discovery takes place. And perhaps that's the deepest comfort of all. We live in a universe that has boundaries, but within those boundaries we're free to explore, to learn, and to create. The limits don't tell us what to think, or what to imagine, or what to dream. They simply tell us the stage we're standing on. The rest, the curiosity, the creativity, the search for meaning, yes, is entirely up to us. Even if we never reach some of the horizons we've talked about, we can still aim toward them. The journey doesn't lose value because the destination is unreachable. In fact, sometimes the unreachable goals are the ones that shape us the most, giving our efforts a direction, and our questions a depth they wouldn't otherwise have. The comfort of limits isn't about settling for less. It's about understanding that the shape of the possible is part of what makes the possible worth pursuing. The cosmos is vast, but it's also structured, and in that structure there's a kind of quiet assurance, a promise that while we may never know everything, we will always have something worth knowing. And so we continue, not in defiance of the limits, but because of them. Each new discovery fits into the framework they provide, adding another detail to the picture. The edges remain steady and unshaken as the picture itself grows richer. And in that ever-growing picture, we find our place, not as creatures trapped by boundaries, but as explorers shaped by them. And that brings us to the end of tonight's journey. We've wandered through the far edges of what's possible, tracing the outlines of the universe's boundaries, and finding not just barriers, but the quiet reassurance they offer. If you found this a soothing way to drift through big ideas, you can always return, and we'll explore something new together. Until then, let the mind settle, let the questions rest for now, and allow yourself to drift into that peaceful space where the universe feels both vast and comfortably close. Sleep well.